Imagine standing at the edge of everything and realizing there might still be more beyond it. Every telescope ever built, every map of galaxies and light, only shows us a small bubble of space that we can see. But outside that bubble could be an endless stretch of unknown reality, perhaps with other universes, other laws of nature, or even different versions of existence. Could another universe be so close that it touches ours without us ever knowing? Or is there truly nothing beyond, just the silence of infinite emptiness? The search for answers has led scientists to the very limits of knowledge, where the border between reality and possibility begins to blur. The edge that shouldn't exist. The phrase "the edge of the universe" might conjure the image of something solid and final, a kind of invisible border where everything stops. It's an image that fits our everyday way of thinking. Every ocean has a shore, every map has a border, every road eventually ends. So when we think about the universe, our minds almost instinctively search for an edge, a point where the stars fade into nothing, where space itself runs out. But when scientists talk about the structure of the universe, they describe something stranger. They tell us that the universe doesn't have an edge at all, at least not in any way we can picture. Space doesn't end. It bends, expands, and continues, perhaps forever. And that simple idea, that the universe can be finite yet have no boundary, might be one of the hardest truths for the human mind to accept. It helps to remember that the edge we're talking about isn't a physical place we can travel to. The universe isn't like a giant sphere floating in empty space. There's no outside we could stand in and look back at it from afar. When scientists say the universe is expanding, it's not expanding into something else. The expansion is of space itself. Every point in the universe moves away from every other point as the fabric of space stretches. This means there isn't a center or an outer rim, only an everywhere that keeps growing. So if you were to head in one direction forever, you wouldn't reach a wall. You might instead curve back around, ending up where you started, much like walking endlessly on the surface of a sphere. That idea, that you can keep moving and never find an edge, comes from a deep truth about geometry and space. The universe could be finite, meaning it contains a certain amount of matter and energy, yet still have no boundary. The Earth's surface is a familiar example. If you travel far enough in one direction, you don't fall off the planet, you just circle back. The cosmos might work in a similar way, but in higher dimensions. Space might curve around itself, creating a shape that has no edges but still encloses everything. Scientists call this a closed universe. In such a universe, there is no border, no endpoint, just a continuous, self-contained space where every direction leads you back into more of the same. However, even if space itself has no physical edge, we do encounter a kind of limit, the edge of what we can see. Light takes time to travel, and because the universe has a finite age, about 13.8 billion years, we can only observe light that has had time to reach us since the beginning. That forms what's known as the observable universe, a vast bubble around us roughly 93 billion light-years across. Beyond that bubble, there's likely more universe, perhaps infinitely more, but its light hasn't reached us yet. So when people talk about the edge of the universe, what they really mean is the edge of the observable part, not a wall, but a horizon. It's the farthest distance from which light can have traveled to us since time began. Beyond it, the universe keeps going, unseen and possibly unknowable. But for most of us, that explanation feels incomplete. We want to know what's beyond even that horizon. What lies outside the visible bubble? If there's more space, where does it end? This desire to find an edge is a reflection of how our minds evolved. We live in a world defined by borders. Every place we've ever known has edges, boundaries, and transitions. The idea of something endless, something with no outside or limit, feels unnatural. Even when told that the universe has no edge, we can't help but imagine one. A glowing rim, a curtain of stars, or a dark void stretching beyond everything. Einstein's theory of general relativity gave us the best framework yet for understanding why there's no edge. It describes space and time as part of a single, flexible fabric that can curve and stretch under the influence of matter and energy. The equations allow for universes that are finite but unbounded. To visualize this, some physicists use the analogy of a balloon. Imagine tiny dots drawn on its surface. As the balloon inflates, the dots move away from each other, just like galaxies receding in an expanding universe. But there's no point on the balloon surface that marks an edge. The surface itself is all there is. Still, this balloon analogy only works up to a point. It shows how expansion works, but not what it means for the universe to have no outside. We can picture the balloon floating in a larger space, but that larger space doesn't actually exist for the universe itself. There's no surrounding void or beyond for it to expand into. The balloon surface is all of reality in this analogy. That's the part that feels impossible to imagine. Because everything in our experience happens within some kind of larger container. The universe seems to break that rule, existing as the container for everything, with nothing outside to contain it. There are other models of the universe that challenge our sense of edges in different ways. Some versions of cosmology suggest that space could be flat and infinite, stretching endlessly in all directions. Others propose a shape that loops back on itself in complex, multi-dimensional ways, so traveling far enough in one direction could eventually bring you back from another. There's even the idea that the universe might be part of a larger multiverse, a vast cosmic landscape where countless universes exist side by side, each with its own laws and boundaries. If that's true, then what we call the universe might actually have an edge after all, but one that leads not into nothingness, but into another universe entirely. Whatever the truth, our human instinct to imagine an edge reveals something about how we think. We need boundaries to make sense of things. They give structure to our ideas, shape to our fears, and comfort to our understanding. Without them, everything becomes harder to picture. The concept of infinity, for example, is easy to describe in words, but nearly impossible to grasp emotionally. It feels empty, unsettling, almost too big to fit in the mind. When scientists say space has no edge, they are describing something that may be correct mathematically, but still profoundly alien to human intuition. And yet, even though we know the universe has no wall, we keep searching for one. Our telescopes reach farther, our models grow more precise, our maps of the cosmos become ever more complete. We've traced the faint afterglow of the Big Bang, the cosmic microwave background, or CMB, to its limits, revealing a kind of cosmic horizon that surrounds us on all sides. We can see back almost to the beginning of time itself, but no matter how far we look, we never find the edge we expect. What we find instead is more of the same, more galaxies, more structure, more mystery. It's as though the universe is gently reminding us that the limits we see are not the limits of reality, but of our vision. The universe as a self-contained horizon. Everything we've ever known, every galaxy, every star, every atom, exists within a finite sphere of visibility. Yet, logically, there's no reason to believe that reality ends there. The universe could continue endlessly beyond our horizon, filled with countless other galaxies, other structures, perhaps even other cosmic histories. But we'll never be able to prove it, because their light will never reach us. The observable universe isn't the universe itself. It's just the part of it that time allows us to see. This horizon is not static. It changes as the universe ages. Billions of years from now, galaxies near the edge of visibility will slip beyond our reach. The accelerating expansion driven by dark energy is causing distant galaxies to move away faster and faster, until even their ancient light can no longer make it across the widening gulf. In the far future, observers in our galaxy may find themselves in a lonely cosmos, where all other galaxies have vanished from sight. Their horizon will shrink, and their picture of reality will become smaller, even though the universe itself continues expanding endlessly beyond their view. It's a humbling thought, that the universe we see today is just a temporary glimpse, a snapshot of a larger reality that constantly recedes from us. Scientists use the CMB to map the farthest reaches of our horizon. It's the oldest light we can detect, released when the universe was only about 380,000 years old. Before that, the cosmos was so hot and dense that light couldn't travel freely. It scattered endlessly among charged particles. When the universe cooled enough for atoms to form, light broke free and began its long journey across space. That ancient glow now bathes the universe in every direction, stretched into microwaves by billions of years of expansion. It forms the ultimate wall of sight. Beyond it, we can't see directly, because light simply couldn't exist in the form we know it yet. And yet, the CMB doesn't mark an end. It's more like a fog that limits our view, hiding whatever lies before the universe became transparent. Theorists have tried to peer past it using indirect methods, searching for traces of gravitational waves or subtle patterns in the background radiation that might reveal what happened during the first fraction of a second after the Big Bang. That was the time of cosmic inflation, when the universe is believed to have expanded faster than light, smoothing out its structure and setting the seeds for everything that followed. Inflation would also mean that the universe we can see is just a tiny patch of something much larger, perhaps unimaginably so. In that picture, our observable universe might be like a single grain of sand on an endless beach. The regions beyond our cosmic horizon could be vastly different from what we know, with different arrangements of galaxies, different densities of matter, even slightly different laws of physics. Some cosmologists suspect that our entire observable universe is only one bubble in a much larger cosmic foam, where countless other regions formed from inflationary bursts and grew into separate universes of their own. Those other universes, if they exist, would be completely cut off from us, forever beyond our cosmic horizon. In a way, they'd be just as real, but unreachable, existing in a realm that our light can never touch. For the human mind, this idea creates a strange kind of paradox. We live in what feels like an infinite space, but the universe we can observe is finite. Beyond its edge, there might be infinite continuation, but it's one we can never confirm. The speed of light and the expansion of space together lock us inside our observable bubble, turning it into a kind of cosmic island. Even though this horizon seems to separate us from the rest of reality, it's also what gives structure to our universe. The finite speed of light allows us to see cosmic history unfold in layers. When we look out into deep space, we're seeing back in time, nearby galaxies as they are now, distant galaxies as they were billions of years ago, and the CMB as it was at the dawn of time. Every direction we look is a journey into the past, and the horizon marks the farthest moment we can ever witness. The horizon defines what we mean by the universe. Everything we can measure, predict, and understand exists within it. Beyond it lies a realm we can only speculate about. We may call it part of the universe, but in practice, it's forever beyond science. This also means that our understanding of everything is inherently incomplete. No matter how far our telescopes reach, there will always be more universe beyond them. As technology improves, we push the boundary of what we can see, but the true horizon always lies farther still, unreachable by any means. The cosmic horizon grows in one sense, as time allows light from new regions to reach us, yet the accelerating expansion ensures that other regions are lost forever. Astronomers sometimes describe the observable universe as a causal bubble. Everything inside it can, in principle, affect everything else, either now or in the future. Outside it, causality breaks down. Events there can never influence us. It's a strange, almost claustrophobic realization that our universe, vast as it is a closed system of cause and effect, isolated from the greater reality beyond. And yet, that isolation may be what allows complex structures like galaxies, stars, and life itself to exist. Within this cosmic island, conditions were just right for matter to form and evolve. Perhaps if we were part of a wider, interconnected cosmos with no horizon, the balance that allows us to exist would never have emerged. When we think of the universe as a self-contained horizon, we begin to see how fragile our cosmic perspective really is. Everything we know exists inside a finite window of time and space, a momentary glimpse of a far greater reality. Beyond that horizon, the universe continues to unfold in silence, unseen and untouched, It's light forever traveling but never arriving. It's an eternal reminder that no matter how far we reach, there will always be more beyond our grasp. When expansion outran light. In the first fraction of a second after the Big Bang, something extraordinary happened. The universe didn't just expand, it ballooned. Space itself stretched at a rate so fast that even light, the ultimate cosmic speed limit, couldn't keep up. This brief but powerful phase is known as inflation, and though it lasted for only a tiny sliver of time, perhaps less than a trillionth of a second, it changed the structure of the cosmos forever. It's a moment that defies ordinary understanding, when the universe grew from smaller than an atom to something macroscopic, smooth and vast enough to set the stage for everything we now see in the sky. To understand why inflation matters, it helps to imagine what the universe was like before it began. Right after the Big Bang, the cosmos was filled with unimaginable energy and heat. Quantum fluctuations, tiny random jitters in the fabric of space, constantly rippled through the chaos. But then, something triggered a runaway process. A mysterious form of energy, sometimes called the inflaton field, began to dominate, causing space to expand exponentially. In an instant, distances between points in space grew so fast that any two regions were pulled apart faster than light could travel between them. Nothing in the universe was outrunning light through space. Instead, the stage on which everything exists was expanding beneath them. The effect, however, was the same. Regions that were once connected became permanently separated. Light, no matter how long it traveled, could never bridge the gap. That's how the universe we inhabit came to be filled with countless isolated patches, each one its own little cosmic island, sealed off from the rest by the expansion of space itself. Inflation explains many mysteries that puzzled scientists for decades. One of them is why the universe looks so smooth on large scales. When we look in opposite directions across the sky, we see regions that appear almost identical, the same temperature, the same density, even though, under normal expansion, there hasn't been enough time for light or information to travel between them. Without inflation, that uniformity is hard to explain. But if the universe once expanded faster than light, it makes sense. Before inflation, everything was close enough to interact and share energy. Then, inflation stretched that tiny, connected region to cosmic size, freezing in the uniformity we still see today. Another puzzle inflation helps solve is why the universe appears flat, meaning that, on the largest scales, space isn't curved like a sphere or a saddle, but seems almost perfectly level. Normally, slight irregularities in the early universe should have caused curvature, making the cosmos either closed in on itself or open to infinite expansion. Yet every measurement shows that it's astonishingly flat. Inflation provides a simple answer. Just as blowing up a balloon makes a small patch of rubber seem flatter, blowing up the early universe made any initial curvature imperceptibly small. What we see now is just a tiny, flattened portion of an enormous whole. But inflation didn't just smooth and flatten the universe. It also planted the seeds for everything that would eventually form within it. Those same quantum fluctuations that once rippled through the infant cosmos got stretched by inflation to enormous sizes. Tiny variations in density became the blueprints for galaxies, stars, and planets. When inflation ended and the universe returned to a slower pace of expansion, gravity began pulling those slightly denser regions together, creating the vast web of cosmic structure we see today. In that sense, every galaxy, including our own, owes its existence to the random quantum ripples magnified during those first fleeting moments. Despite how central it is to modern cosmology, inflation remains one of the most mysterious ideas in science. We don't yet know what caused it, or what exactly the inflaton field was. Some theories suggest it could have been a property of space itself, a kind of vacuum energy that temporarily filled the universe and then decayed, releasing the matter and radiation that formed everything we know. Others see inflation as a natural consequence of quantum physics operating on a cosmic scale. Whatever the cause, the result was a universe that expanded faster than anything we can truly imagine. What makes inflation even more intriguing is what it might have left behind. The theory predicts that inflation didn't necessarily stop everywhere at once. In some regions, the expansion may have slowed and ended, forming bubbles of space like ours. In others, inflation may have continued, endlessly creating new bubbles, each one expanding into its own universe, disconnected from the rest. In this eternal inflation idea, the process that created our cosmos never truly stopped. It just keeps producing new universes in a vast cosmic sea, forever beyond each other's horizons. If eternal inflation is real, then our universe is just one of countless others, each with its own physical properties, laws, and histories. Some might be nearly identical to ours, with stars and galaxies that follow the same patterns. Others might be wildly different. Universes with different constants of nature, where matter behaves in alien ways or where time unfolds differently. In that picture, there's no single Big Bang, but an ongoing process of cosmic birth, where universes bud off from an inflating background like bubbles in boiling water. It's a vision of reality so enormous that our entire observable cosmos becomes a small and ordinary feature within something much greater. For most of human history, people assumed the universe was a single continuous whole, everything that exists, bound together in one vast space. Inflation challenges that intuition. It suggests that what we call the universe might just be our own small patch of a much larger, eternally expanding structure. The regions beyond our horizon aren't just out of sight, they may be completely separate realms, cut off forever by the unstoppable expansion of the cosmic fabric itself. Light from those places will never reach us, and no probe or traveler could ever cross the divide. The distances grow too fast, the expansion too relentless. What began as a single burst of creation may have fragmented into countless self-contained worlds, each evolving on its own. It's hard to picture what that really means. Imagine an infinite field of space bubbling with universes. Each bubble expands, cools, and develops its own galaxies and stars, but they can never touch. From inside, each universe looks like all there is, an infinite expanse in every direction. But seen from a higher perspective, it's just one among many. Inflation turns the idea of a singular cosmos into something more like a vast, self-replicating landscape. And within that landscape, every possible version of physics might exist somewhere, realized in some far-off bubble that we can never observe. Scientists search for clues of inflation's legacy in the oldest light we can see, the CMB. The pattern of tiny temperature variations across that ancient glow carries the fingerprints of inflation's quantum fluctuations. So far, those patterns match predictions almost perfectly, giving strong support to the theory. But the direct evidence, the detection of primordial gravitational waves rippling through that early universe, still eludes us. If we ever find them, they would be a direct echo from that moment when expansion outran light, a message from the first instant of everything. Inflation might still be happening right now, somewhere far beyond what we can see, giving birth to new universes as we speak. Each one forever separate, yet all part of the same grand, unending process that began when time itself was born. The cosmic mirage. Imagine looking into a curved mirror. What you see looks real, detailed, and complete, yet it isn't quite what it seems. Distances warp, shapes stretch, and objects that are far apart appear closer together. This kind of illusion is familiar to us in everyday life, but something very similar might be happening on the grandest scale. Some physicists believe that our universe could be a kind of cosmic mirage. In this view, what we perceive as a vast three-dimensional cosmos might actually be a projection or a curved representation of something existing in higher dimensions. We could be living inside an image, unaware that the light, gravity, and structure we see are shaped by a reality that lies beyond our perception. The idea that our universe might be a projection sounds strange, but it comes from serious attempts to understand how space, gravity, and information really work. One of the biggest clues comes from black holes. When a massive star collapses, it forms a region where gravity is so strong that nothing, not even light, can escape. Yet, according to physics, information, the fundamental description of everything that exists, can never be truly destroyed. So where does the information about everything that fell into a black hole go? The answer may lie on its surface. Decades ago, scientists discovered that a black hole's entropy, its measure of hidden information, is proportional not to its volume, but to the area of its event horizon. That finding was shocking. It suggested that everything inside a black hole could be described by data encoded on its outer boundary. From that strange insight came a revolutionary idea, the holographic principle. It proposes that the entire three-dimensional universe might be describable by information written on a distant, two-dimensional surface, just like a hologram, where a flat sheet of patterns produces a 3D image when illuminated. If that principle holds true, then everything we experience, every star, planet, and atom, could be the result of information projected from a deeper, higher dimensional reality. We wouldn't be able to see that higher realm directly, just as a shadow can't perceive the object that casts it. To us, it would appear that space, time, and matter are self-contained. But in truth, they might be part of a larger structure whose full form we can never see. Even without invoking the holographic idea, gravity itself creates illusions on a cosmic scale. Light doesn't always travel in straight lines. In regions where space is curved by massive objects like galaxies or clusters of galaxies, light bends. This phenomenon, called gravitational lensing, can magnify and distort the light from more distant galaxies. Sometimes it produces arcs or rings of light that trick us into thinking we're seeing something unique, when we're really seeing multiple images of the same object. To an observer unaware of the bending, the universe might appear perfectly normal, even though the geometry of space is twisting their view. On cosmic scales, such distortions may be happening everywhere, creating a vast mirage of stretched and bent light that subtly reshapes our picture of reality. If the entire universe is curved, not just by local masses, but by its overall shape, then every bit of light we see from the distant past is bent by that curvature. This means our view of the cosmos could be warped. Galaxies that seem far apart might actually be closer in some hidden dimension. What appears flat might really be wrapped around itself. The light from the early universe could be circling through a curved geometry, giving us a false sense of completeness. We might be looking at one portion of a much larger cosmic structure, like an ant crawling across a balloon, convinced the curved surface is all there is. General relativity already tells us that mass and energy bend space and time, but some scientists believe that the geometry we observe could itself be just a shadow of higher dimensional curvature. In certain cosmological models, our entire universe is thought to exist on a three-dimensional brane, a kind of surface, floating within a higher dimensional space known as the bulk. According to this view, gravity might leak slightly into those extra dimensions, explaining why it's so much weaker than the other forces of nature. The light and matter we see would be confined to our brain, giving us the illusion of a self-contained universe, even though, in truth, we're part of something far more complex. In this picture, the edge of the observable universe might not be a true limit, but a kind of visual boundary created by the way light and gravity behave within our brain. Beyond that edge, in the bulk, space could continue in directions we can't perceive, not outward, but orthogonally, into dimensions that our senses and instruments are blind to. To us, the cosmos would appear to end smoothly, like the horizon of the ocean, even though the larger structure keeps going. We might be trapped in a cosmic perspective shaped by our own dimensional limits, mistaking the projection for the whole of reality. The more scientists study light from the farthest reaches of space, the more subtle distortions they find. Some galaxies appear duplicated, stretched, or smeared into arcs. Gravitational lensing from massive structures between us and them explains much of it, but there could be deeper layers of illusion. If the universe's geometry itself is curved by unseen dimensions, then every beam of light is carrying hidden information about that curvature. By mapping these distortions carefully, cosmologists can infer the invisible structure of space, like cartographers tracing a landscape by studying the flow of its rivers. In doing so, they might be glimpsing hints of a higher dimensional reality, even if they can never see it directly. There's another layer to this cosmic mirage, one rooted in quantum theory. Quantum mechanics tells us that particles and waves are not separate things but two sides of the same reality, depending on how they're observed. On cosmic scales, that interplay could apply to space itself. Some theories suggest that spacetime might be a kind of emergent phenomenon, something that arises from deeper quantum interactions, much as a holographic image arises from light interference. In that sense, space and time might not be fundamental at all, but illusions created by the way information is organized in the universe. If that's true, then everything we see could be a large-scale projection of an underlying informational structure we can't perceive. Astronomers already see hints that our universe might not be as straightforward as it looks. The CMB shows subtle temperature variations across the sky. These tiny differences form a pattern that scientists use to measure the universe's geometry. For the most part, it appears flat. But there are anomalies, slight asymmetries and alignments that don't fit perfectly with a simple, uniform model. Some have speculated that these irregularities could be signs of a larger curvature or hidden structure, perhaps even evidence that our observable universe is part of a bigger whole. Others think they're statistical flukes, artifacts of measurement. But if they're real, they might be the faint fingerprints of a reality curving just beyond our reach. Even the way we perceive cosmic time could be part of the mirage. In relativity, time and space are interwoven, and the curvature of one affects the flow of the other. If our universe is curved within a higher dimensional framework, then what we call cosmic time might be a projection as well, a reflection of deeper, unseen dynamics. What we experience as the expansion of the universe could be, in some larger sense, the shadow of higher dimensional motion. The entire cosmic story, from the Big Bang to the present, might be one perspective within a far greater tapestry that exists beyond our comprehension. For the human mind, these ideas are difficult to hold on to. We experience the universe as solid and continuous, a place filled with stars, matter, and measurable distances. But if the cosmic mirage idea is right, what we see is only the visible face of a much larger, multidimensional truth. Every photon of light might carry within it a faint signature of that hidden geometry, just as a reflection carries clues about the shape of the mirror it came from. When we look into the night sky, we might be gazing not at the full extent of reality, but at a projection, a curved and distorted image of something that transcends our senses entirely. Everything we can know, every law of physics we've discovered, might be the language of that projection. The cosmos could be far larger, more complex, and more beautiful than we can ever perceive, and all we will ever see of it is the glowing mirage that unfolds before us. The silent bang. When we imagine the Big Bang, the mind fills with light and sound, a brilliant flash, a roar of creation, an explosion scattering matter into the void. But this picture, while poetic, is not what physics describes. There was no blast echoing through space, because space itself did not yet exist. There was no outside, no background against which the event could unfold. In many ways, the Big Bang wasn't an explosion in space, but an expansion of space. And some theories go further, suggesting that even the term bang might be misleading. What if our universe began not with fire and noise, but with something closer to a whisper, a transition so gentle it might be called a silent bang? In the traditional view, the universe started from an extremely hot, dense state. But this story leaves open the question of what came before, or what triggered that state to appear. As physicists probe deeper into the nature of quantum fields, they began to suspect that the Big Bang might not have been a singular beginning at all. Instead, it could have been a smooth shift in the underlying energy of reality, a transformation rather than a creation. Imagine a calm landscape of potential energy, like a still field stretching in every direction. For reasons still unknown, that energy might not have been perfectly stable. A tiny fluctuation, a quantum tremor, could have caused it to roll into a new configuration, a bit like water freezing into ice. In this transition, the structure of space-time itself could have changed, releasing energy that expanded and cooled into the universe we know. No explosion, no chaos, just a change in the state of existence. This kind of transformation is often called a phase transition, and we see similar behavior in simpler systems. When steam condenses into droplets of water, it releases heat. When water freezes, it gives off energy too. If the fabric of the cosmos behaved in a comparable way, the birth of a universe might simply be the cosmos changing form. In this sense, the Big Bang was not the beginning of everything. It was the moment when everything became what it is now. The remarkable part of this idea is that such transitions could happen many times, in many places. If the vacuum of reality, the underlying quantum field that pervades everything, has multiple stable states, it's possible that different regions could fall into different configurations. Each transition would create its own pocket of space-time, expanding outward independently. From the perspective of any observer inside one of these pockets, it would look like their universe had begun with a Big Bang. But from a larger view, it would be one of countless silent births unfolding across the endless landscape of potential reality. This framework is sometimes referred to as the multiverse from the quantum vacuum. Unlike the bubble universes that form through inflation, these universes don't grow from expanding patches of space, but from quantum transitions occurring wherever conditions allow. Each is born from silence, a localized shift in energy, not an explosive event. The process could be continuous, eternal, and unending, with new universes forming as old ones fade away. If true, this picture redefines what we mean by creation. Instead of a single point of origin, existence becomes a network of births, each one emerging from the quiet background of the quantum field. Every universe becomes both a child and a sibling, part of an infinite family of realities that coexist yet never touch. And all of them would trace their lineage back not to an explosion, but to a silent and seamless transformation of energy. This view also offers a way to think about what came before our universe without invoking impossible infinities. Before our Big Bang, there may not have been nothing. There may have been a prior vacuum state, different from our own, stable for a time, but destined to change. When it did, it set off the chain of events that became our cosmos. In that sense, our universe could be the latest in a long line of transitions, each one birthing a new phase of reality from the decay of the last. One implication of this idea is that the Big Bang, as we perceive it, might not be unique. There could have been others before, or others happening right now, in places beyond any possible observation. The quiet birth of universes might be an ongoing process, a continuous renewal of reality. Quantum cosmology gives this concept a mathematical foundation. According to some models, the vacuum of space is never truly empty. It seethes with energy fluctuations, temporary appearances of particles that wink in and out of existence. Over enormous timescales, these fluctuations might cause regions of space to tunnel into new states of being, essentially popping into existence as self-contained universes. The process would be random, but not impossible. Given infinite time, it would happen endlessly. This means our own universe may have been born out of quantum inevitability rather than a deliberate cause. It didn't need an external trigger because the very nature of reality allows for such transitions to occur spontaneously. In a sense, existence is self-generating. The silence of the bang is the sound of physics unfolding according to its own principles. If universes can arise from quiet fluctuations in energy, does that mean reality is constantly creating itself? The answer, in a way, is yes. Each quantum field has built-in uncertainty, a fundamental restlessness that ensures change is always possible. Even in what seems like perfect stillness, there's motion on the tiniest scales. From that motion, over infinite time, new spacetimes can emerge. What we see as the calm emptiness between galaxies might, on the grandest scales, be part of an endless background of creation. For us, bound within one such bubble, this process is invisible. We see only the aftermath, the expanding universe, the background radiation, the galaxies drifting apart. But those might be just local effects of a far larger and quieter process. The cosmic silence we hear when we look into deep space may not be the absence of sound, but the hum of transition, the silent afterglow of creation continuing far beyond our ability to detect. There's something deeply human about the need to assign drama to beginnings. We imagine fire and chaos, divine commands or bursts of light. Yet the more we study the cosmos, the more it seems that creation may be the opposite of violent. The early universe, though unimaginably energetic, may have begun with a soft and ordered transformation. In the language of physics, silence doesn't mean stillness, it means harmony, energy finding balance, fields settling into form. The silent bang represents this harmony, a cosmic event that was immense yet smooth, sudden yet calm, birthing time and space through transition. It's a strange thought that the beginning of everything might have felt, from an outside view, like nothing at all. No light to flash across an empty sky. Just an invisible shift in the structure of what was possible, and from that, the slow unfolding of everything that would ever be. And if this process is ongoing, then even now, new universes may be blooming in the unseen corners of the cosmic field, expanding in their own directions, following their own rules, unaware of us as we are unaware of them. Quantum foam and unfinished space. If we could somehow shrink ourselves down to the smallest possible scale, far smaller than an atom, smaller than a proton, smaller than even the particles that make up those particles, the world we know would dissolve into something entirely unrecognizable. The smooth fabric of space that appears continuous and calm from our point of view would no longer look like a flat, stable expanse. It would seethe, it would flicker, it would foam. This is what some physicists call quantum foam, the restless chaos that might exist at the foundation of reality. At scales this tiny, the very idea of space becomes uncertain. Distances lose their meaning. The laws of physics, which seem so reliable in everyday life, begin to blur together. Gravity and quantum mechanics, the two great frameworks of modern science, collide here, and neither fully describes what happens. According to quantum theory, energy and particles can never be perfectly still. They fluctuate constantly, borrowing energy from the vacuum for the briefest of moments before giving it back. These fluctuations are everywhere, at every instant, occurring on unimaginably small scales. Now imagine those fluctuations not just affecting matter and light, but the geometry of space. Tiny regions of spacetime might momentarily curve, twist or fold in on themselves, like bubbles forming and collapsing in boiling water. These ephemeral distortions could create fleeting pockets of spacetime, miniature universes that flicker into existence and vanish before they can grow large enough to persist. This view paints reality not as a calm ocean, but as a stormy surface of ceaseless creation and annihilation, where existence itself never truly settles. The term quantum foam was first coined by the physicist John Wheeler in the 1950s, as he tried to imagine what spacetime would look like near the so-called Planck scale, a distance of about 10 to the power of -35 meters. At that scale, quantum uncertainty is so extreme that space and time themselves stop behaving as continuous quantities. Instead, they might appear as a frothy mess of constantly changing geometry, full of energy fluctuations powerful enough to momentarily warp the structure of the cosmos. In this foamy chaos, gravity would no longer behave smoothly as Einstein's equations describe. Instead, the smooth curvature of spacetime that general relativity predicts might break down entirely, replaced by something far more granular. It's as if space were not a solid sheet, but a bubbling surface, where tiny bursts of geometry pop in and out of existence every fraction of a second. And within that froth, it is possible, at least theoretically, that some of those bubbles might expand instead of collapsing. If a quantum fluctuation happens to create a tiny region of space with just the right conditions, enough energy density, the right vacuum state, it could start to expand outward. Normally, such fluctuations collapse too quickly to matter, vanishing back into the vacuum before they can grow. But if the laws of physics allow for inflationary expansion to take over, that tiny bubble could swell exponentially, breaking away from the quantum foam and becoming its own self-contained universe. This possibility connects deeply with earlier ideas about eternal inflation and multiverse theory. It suggests that universes might not only form from transitions in large cosmic fields, but also from the smallest fluctuations imaginable, the quantum tremors at the base of existence. Every moment, in the endless foam of spacetime, the seeds of new universes might be appearing. Most vanish instantly, but perhaps, once in an eternity, one grows large enough to escape the pull of its own instability and expand forever. Our own Big Bang could have been born from just such a fluctuation. In this way, quantum foam could be the ultimate source of creation itself, the foundation on which all space, time, and matter arise. What appears solid and continuous on cosmic scales may be at its root an ocean of constant motion, where existence flickers between being and non-being at unimaginable speeds. The challenge, of course, is that this realm lies far beyond our ability to probe directly. No telescope can peer into scales that small, and no particle accelerator can reach energies that high. Even our most advanced theories struggle to describe what happens there. The mathematics of quantum mechanics and general relativity break down under the intense curvature and uncertainty of the Planck scale. To make sense of it, physicists have turned to theories that attempt to unify these two pillars of science, such as string theory and loop quantum gravity. String theory, for instance, proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings, each oscillation defining a particle's mass and charge. Within this framework, spacetime itself could emerge from the interactions of these strings. The foam-like behavior Wheeler imagined might then be the collective vibration of countless microscopic strings shaping the texture of space. Similarly, loop quantum gravity envisions spacetime as being woven from finite loops, forming a kind of quantum fabric. At very small scales, this fabric would fluctuate wildly, giving rise to the foamy structure predicted by Wheeler. Despite their differences, both ideas converge on the notion that space is not smooth, nor is it static. It is a dynamic medium, alive with energy and constantly evolving, even at its smallest levels. The calm expanse of the cosmos that stretches between galaxies could be an illusion of scale, a large-scale calm concealing a small-scale storm. If new universes can form spontaneously from quantum foam, then creation itself might not require a beginning. Reality could be self-sustaining, constantly birthing new pockets of existence from its own underlying restlessness. The boundary between something and nothing would blur, replaced by a continuum of possibilities bubbling in and out of being. The void, in this picture, is not empty at all. It's the most active, fertile thing imaginable. The hidden architectures beyond our horizon. When a map of the CMB was first produced in detail by satellites like COBE, WMAP, and later the Planck spacecraft, it showed a pattern of tiny temperature fluctuations, mere millionths of a degree. These variations weren't random noise, they were the seeds from which galaxies, stars, and planets would eventually grow. Yet, hidden within this delicate pattern were subtle anomalies, features that didn't quite fit the expected model of a perfectly uniform early universe. These irregularities have become one of the most intriguing puzzles in modern cosmology, hinting that there might be more beyond our observable horizon than we ever imagined. One of the first peculiarities scientists noticed was what they called the cold spot, a large region of the CMB slightly cooler than the surrounding areas. It's far larger than the random variations predicted by standard inflationary models. At first, many thought it might be a statistical fluke, or perhaps caused by foreground effects, like intervening galaxies absorbing or scattering radiation. But as data improved, the cold spot persisted. It didn't disappear with better instruments or refined analysis. That persistence opened the door to more speculative interpretations. Could it be a sign that our universe once brushed against another? If the multiverse is real, then occasionally two bubbles might collide, their boundaries interacting for a brief moment before drifting apart again. Such a collision would leave an imprint, a circular distortion or temperature anomaly, on the CMB. In theory, it could appear as a cold or hot region, depending on the relative energy conditions between the two universes. The cold spot, with its unusual size and depth, fits the general expectation of such a cosmic scar. Physicists have spent years studying the CMB, looking for evidence of these cosmic fingerprints. The search is delicate, almost forensic in nature. Researchers use statistical algorithms to analyze the distribution of temperature variations across the entire sky, trying to separate ordinary quantum fluctuations from potential signs of something more profound. They look for circular symmetry, subtle gradients or repeating patterns, any indication that the early universe was influenced by an external force. Some analyses have hinted at patterns that don't align with randomness, while others find no compelling signal. Another intriguing anomaly lies in what's called the axis of evil, a curious alignment of large-scale fluctuations in the CMB. In theory, the universe should look statistically the same in all directions, with no preferred orientation. But when cosmologists examined the data, they found that certain temperature features appear to line up across the sky, as if the cosmos had a hidden structure or axis. This could be coincidence, an artifact of observation, or perhaps a sign that something beyond our horizon subtly influences the geometry of space itself. If the universe is part of a larger multiverse, neighboring regions could gravitationally distort ours in ways that show up as such alignments. There are other possible fingerprints too. Some theories predict that gravitational waves could carry signatures of interactions between universes. These waves would leave characteristic polarization patterns in the CMB, twisting the orientation of its light. Experiments like BICEP and the South Pole Telescope have been searching for these B modes, a specific pattern of polarization that could confirm the presence of primordial gravitational waves. While earlier results sparked excitement, they were later found to be contaminated by interstellar dust. Still, the search continues, because finding these patterns could not only confirm inflation, but also hint at whether our patch of the cosmos was ever disturbed by something beyond it. Some physicists suggest that our universe might be surrounded by a vast, hidden cosmic architecture, structures that exist beyond the horizon but still exert faint gravitational influence on what we can observe. In this view, our observable universe is like a room in a much larger house. We can't see beyond the walls, but we can feel subtle vibrations through them. If another massive region or universe exists just outside our view, it might tug on matter in ours, slightly distorting the large-scale flow of galaxies. Indeed, astronomers have observed mysterious large-scale motions, sometimes referred to as the dark flow, where clusters of galaxies seem to be drifting in a common direction, faster than expected. One possible explanation is that something outside our visible universe is pulling on them. These ideas remain speculative, but they serve as reminders that the universe's horizon is not a physical boundary. The CMB is like a veil, faint, ancient, and full of whispers from epochs we can never directly witness. If there are other universes or colossal structures beyond, their fingerprints might be faint but not invisible. With each new generation of instruments, we peel away another layer of that veil, refining our picture of the early cosmos and searching for the smallest deviations that might tell us there's more beyond. The Planck satellite, launched in 2009, provided the most detailed CMB map ever created, measuring temperature differences as small as 1 part in 100 million. Its data confirmed much of the inflationary model, the overall geometry, the statistical distribution of fluctuations, but it also reaffirmed that strange anomalies exist. The cold spot remained. The axis of evil persisted, though its significance is debated. These features may eventually find mundane explanations, Perhaps they're results of statistical chance or unaccounted astrophysical processes, but if even one of them turns out to be genuine evidence of something beyond our universe, it would revolutionize cosmology. Beyond temperature and polarization, some researchers are also exploring the possibility that our universe's large-scale structure, the distribution of galaxies and voids, could carry echoes of external influences. The cosmic web, the vast network of filaments and clusters that make up the universe's architecture, might not be entirely self-contained. If regions beyond our horizon have slightly different densities or gravitational fields, they could subtly bias how matter clumped together in our universe's early days. Mapping these deviations requires immense computational models and galaxy surveys covering billions of light-years. Projects like the Dark Energy Survey and Euclid mission aim to chart this cosmic structure in unprecedented detail, offering potential new windows into what lies beyond our view. It's a strange irony that the clues to what lies outside our universe might be imprinted in the smallest details of the oldest light. Each temperature fluctuation in the CMB represents a kind of fossil, a preserved moment from when the universe was young, frozen into the cosmic fabric. Decoding these fossils is like reconstructing the shape of a landscape you can't directly see, using only the echoes of its earliest rumblings. To many cosmologists, this pursuit is as philosophical as it is scientific. We're not merely mapping the cosmos, we're testing the limits of what can be known. The idea that other universes might leave fingerprints on ours transforms the concept of reality itself. It suggests that even if we can't step beyond our cosmic horizon, the universe may still be whispering about what lies there. The task is to listen closely enough, to refine our instruments, our mathematics and our imagination until we can read those whispers for what they truly are. As telescopes grow more sensitive and computational models more precise, the patterns in the CMB will continue to be scrutinized. Perhaps future missions will reveal faint ring-like imprints, confirming that our universe once brushed against another. Or perhaps they'll expose even deeper structures, a faint asymmetry, a directional bias or polarization traces that rewrite our understanding of cosmic history. For now, the CMB remains both a map and a mystery. Cosmic recycling before the bang. The story of the universe has long been told as a singular event, yet not everyone has been content with this idea of a single creation. For some physicists, the Big Bang might not have been the ultimate beginning, but merely one chapter in a far longer and recurring cosmic cycle. The notion that the universe could die and be reborn, expanding, collapsing, and emerging anew, has persisted for nearly a century, finding new life with every generation of cosmologists who wonder if the cosmos itself might be eternal, forever recycling its own existence. The earliest hints of such thinking emerged not long after the Big Bang theory itself was proposed. In the mid-20th century, before the CMB had been discovered, some scientists questioned the very need for a beginning at all. The idea that time and space simply erupted from nothing seemed philosophically unsatisfying, even unnatural. It implied that the universe had a sharp, finite origin, a boundary in time where physics itself broke down. To many, that felt incomplete, an unsolved riddle hiding behind the language of mathematics. From that discomfort came the first versions of the cyclic universe. One of the earliest was proposed by the mathematician Richard Tolman in the 1930s, who imagined a cosmos that oscillated endlessly between big bangs and big crunches. In his view, the universe would expand from a singularity, reach a maximum size, then gravity would pull everything back together, collapsing it once again into a dense, hot state. That collapse would set the stage for another explosive rebirth, a new Big Bang. Over cosmic timescales, this cycle could repeat endlessly, with each universe giving way to the next. Tolman even attempted to calculate how entropy, the gradual increase of disorder, might accumulate over cycles, potentially making each expansion slightly larger and longer than the one before. For decades, the idea faded into the background as evidence for the accelerating expansion of the universe emerged. if the cosmos were expanding faster and faster, then it would never collapse again. The discovery of dark energy in the late 1990s, driving that acceleration, seemed to kill off the old oscillating models entirely. Yet the concept refused to die. Instead, it evolved. Cosmologists began to ask whether cyclic behavior could occur even in a universe that never fully collapses. A kind of cosmic recycling that doesn't depend on a total reversal of expansion, but instead happens through transformations of energy and space at quantum scales. One of the most striking modern versions of cyclic cosmology came from the work of Paul Steinhardt and Neil Turok in the early 2000s. Their Ekpyrotic model, inspired partly by ideas from string theory, suggested that the Big Bang was not a true beginning, but the result of a collision between two higher dimensional branes. In this view, our universe might be just one of these branes, floating parallel to another in a higher dimensional space, aka the bulk. Every few trillion years, these branes could collide, releasing an enormous burst of energy that creates the matter and radiation we associate with a new universe. After expanding and cooling for eons, the branes would drift apart again, only to be drawn back together later, triggering another cycle. This version of cyclic cosmology offered an elegant way to sidestep the problem of the singularity, the point of infinite density at the Big Bang, where known physics breaks down. In the Ekpyrotic model, there is no singularity at all, only a transition, one collision leading smoothly to the next. The universe doesn't begin or end, it transforms. Each cycle erases most traces of the previous one, but not entirely. Some physicists speculate that subtle imprints from past cycles could remain in the CMB. Another idea, known as conformal cyclic cosmology, comes from the mathematical physicist Roger Penrose. Penrose's version is perhaps even more radical. He proposed that the far future of our universe, after all matter has decayed and black holes have evaporated, will become indistinguishable from the conditions of the Big Bang itself. In that distant future, the universe would be empty of matter but filled with low-energy radiation. Without mass to define scale or time, the geometry of spacetime would stretch infinitely, and in that strange limit, the end of one universe would naturally blend into the beginning of another. In this framework, the Big Bang wasn't a singular starting point, but the continuation of a previous eon, an earlier universe that had already lived and died. What makes Penrose's idea remarkable is that it predicts something potentially observable. If black holes from a previous eon evaporated through Hawking radiation before the next Big Bang, their final bursts of energy might leave faint circular imprints on the CMB. Penrose and his collaborators have claimed to find such circles, regions of unusually low temperature variation that could, in theory, be remnants of ancient black hole evaporation. The evidence remains controversial, with most of the scientific community unconvinced, but the mere possibility has kept the idea alive. The notion that our universe could bear scars from a time before time is almost too captivating to ignore. Cyclic cosmology also invites a profound shift in how we think about causality. In a one-time Big Bang, everything originates from a single, incomprehensible burst of creation, an event with no precedent. But in a cyclic universe, each new beginning is shaped by what came before. The arrow of time, the distribution of energy, the fundamental constants, all could carry subtle influences from earlier cycles. Could the conditions that allow galaxies, stars, and even life to form be the result of long-term cosmic evolution refined through countless cycles? In that sense, a cyclic universe might act almost like a cosmic memory system. Though each rebirth wipes the slate clean on a large scale, small imprints could persist. The geometry of space, the behavior of quantum fields, or the fine-tuning of constants might carry forward, just as DNA carries traces of past generations. Some physicists have speculated that this could even explain why our universe seems so finely balanced for complexity. It might not be the product of random chance, but of patterns that have repeated and stabilized over unimaginably long timescales. Still, the idea of eternal cycles faces serious challenges. The discovery of dark energy complicates things. If the universe continues accelerating, It may never allow the kind of reversal or reset needed for another Big Bang-like event. Some theorists propose that dark energy itself could evolve, perhaps decaying or changing sign in the distant future, eventually pulling everything back together. Others suggest that new physics could transform expansion into contraction without violating known laws. But until such processes can be demonstrated, cyclic cosmology remains speculative, balanced between elegant possibility and mathematical hope. Quantum gravity, a still developing field, might eventually offer a clearer picture. Some quantum cosmology models suggest that as the universe contracts toward a singularity, quantum effects could create a bounce, preventing total collapse and allowing expansion to begin again. In these models, the Big Bang is not the birth of space and time, but a rebound from a previous phase. Numerical simulations of these quantum bounces even show that certain features, like energy density and curvature, could survive from one cycle to the next. If such theories are right, the Big Bang was just the latest rebirth in an ongoing sequence. The universe could be far older than we think, stretching back through countless cycles, each one rising from the ashes of the last. And somewhere, buried deep in the CMB or in the structure of spacetime, might lie the faintest clues, echoes of earlier universes whispering through the noise of the current one. Every particle could be the recycled material of universes long vanished. The light that travels across space may carry the subtle fingerprints of worlds that no longer exist, and perhaps trillions of years from now, after our own cosmos has expanded, cooled and faded into emptiness, a new burst of creation will occur, not out of nothing, but out of everything that ever was, reshaped and renewed. In a cyclic universe, death and rebirth are not opposites, but partners, each giving rise to the other in an unending rhythm. The brain between worlds. This image of a vast flexible sheet, a brain short for membrane, is one of the most mind-expanding ideas in modern cosmology. It suggests that what we perceive as the entire universe could be just one of many brains existing side by side, each carrying its own version of space, time, and physical laws. These brains might drift through the bulk. We can't see this bulk directly, just as a drawing on a flat page cannot look upward or downward. To us, the universe feels complete, but in this view, it could be merely one surface among countless others. Physicists began to take this idea seriously in the late 1990s, when new versions of string theory, collectively called M-theory, showed that brains could exist in many dimensions. Some of these brains could be as small as subatomic particles, while others could stretch across the scale of an entire cosmos. In this framework, our universe might be a three-dimensional brain embedded in a higher dimensional space, with gravity being the only force able to move between brains. The other forces, electromagnetism, the weak force and the strong force, remain trapped within our own brain, which is why we never feel or see what happens in the others. This concept might sound abstract, but it offers surprisingly concrete explanations for some of the deepest puzzles in physics. For example, gravity has always been a mystery because it's so much weaker than the other fundamental forces. A simple magnet can lift a paperclip against the pull of an entire planet's gravity. But if gravity can leak into extra dimensions, if it's free to move through the bulk while other forces are not, that weakness might make sense. Most of gravity's strength would be spread out across multiple brains, leaving only a faint trace detectable in ours. In brain cosmology, the Big Bang could be reinterpreted as a collision between two brains. Imagine two vast, invisible membranes floating in the higher dimensional bulk. As they drift and ripple, they might occasionally bump into each other. The enormous energy released from such a collision could create a burst of radiation and matter, the beginning of a new universe, from the perspective of observers living within it. The Ekpyrotic model takes this idea further. Each time the brains collide, slightly different conditions might arise. New laws of physics, new constants, new kinds of matter. Our universe might simply be one outcome among countless possible combinations. In the brain model, the higher dimensional bulk is not a static place. It's alive with movement and vibration. Brains can ripple, twist, and stretch, just like the strings that make them up. Those ripples might correspond to gravitational waves or subtle changes in the structure of space itself. And if a brain ripples strongly enough, it could even pinch off, creating a new, smaller brain. Perhaps the seed of a new universe. Perhaps universes are budding off from higher dimensional membranes all the time. Our own brain could have formed from such a process, expanding into a cosmos filled with galaxies, stars, and life. All the result of a brief tremor in a larger unseen dimension. To scientists working on these models, mathematics becomes a kind of telescope. They can't observe the extra dimensions directly, but equations allow them to infer how such a world might behave. Some calculations suggest that interactions between brains could explain why our universe appears to be flat, and why the CMB is so uniform. Others hint that black holes could be windows to the bulk, regions where gravity becomes strong enough to connect our brain to the deeper structure beyond it. The concept has even entered discussions about dark matter and dark energy. If other brains exist nearby, their gravitational pull could subtly influence our universe. Invisible to light but felt through gravity, such neighboring brains might help explain why galaxies move as though surrounded by unseen mass. Similarly, the mysterious energy driving cosmic acceleration could be an effect of the geometry between brains, the tension stretching across the higher dimensional bulk. Yet, despite its elegance, the brain picture remains a hypothesis. It's difficult to test something that might exist in dimensions beyond perception. Most of its predictions lie far beyond the reach of current technology. Still, physicists are developing creative ways to look for indirect evidence. Each potential clue, no matter how subtle, could reshape how we see the universe's architecture. Ghost universes in the fifth dimension. If our universe is a three-dimensional surface embedded in a higher dimensional space, then other universes could exist mere millimeters away, separated not by distance in our familiar sense, but by position along a hidden dimension we cannot perceive. They could overlap perfectly with our own space, sharing every point we occupy and yet remain forever out of reach. Some of these extra dimensions could be curled up so tightly that they're invisible to us, smaller than an atom. Others might be vast, extending infinitely in ways that our instruments cannot detect. Imagine a stack of transparent sheets of glass. Each sheet represents a universe, complete and self-contained, with its own version of space and time. To an observer on one sheet, the others are invisible because light, matter, and all known forces are confined within each separate layer. These ghost universes might have their own galaxies, their own forms of life, perhaps even versions of ourselves following entirely different histories. Yet there would be no way to communicate, no method of crossing the dimensional divide. They would pass through us as though we were mist, their existence hinted only by the faintest gravitational traces. It's possible that some of the unexplained phenomena we attribute to dark matter could be the gravitational fingerprint of matter from one of these neighboring universes. The fifth dimension, beyond the three of space and one of time, could be where these parallel worlds are arranged. We would never see them directly, because our perception is bound to the surface of our own layer. Just as a two-dimensional creature living on a flat surface could never look up or down, we are trapped within the confines of our three-dimensional reality. The fifth dimension isn't a place we could travel to in the normal sense. It's a direction perpendicular to everything we know. If other brains occupy the same physical space but in different dimensions, could there be versions of our own universe with slightly altered histories? Perhaps worlds where events unfolded differently, where stars formed in other patterns, or where life took another path. These would not be distant parallel timelines in the traditional science fiction sense, but literal universes coexisting with ours, their separation not through space or time, but through the structure of higher dimensional geometry. Physicists describe these hidden dimensions using mathematical models known as compactifications. In these, the extra dimensions are tightly curled, like the threads in a woven fabric. But some versions of these models allow for dimensions that are large, even infinite. In those scenarios, brains could stack or float freely, separated by distances measured not in meters or kilometers, but in fractions of a fundamental scale. Distances so small that our most powerful instruments could never detect them. And yet, within those separations could lie entire universes, each with its own vastness. To visualize how such universes might exist simultaneously, think of radio waves. Many stations broadcast through the same space at once, each carrying different sounds and information. You only hear one because your receiver is tuned to a specific frequency. In a similar way, each universe could resonate at its own dimensional frequency, occupying the same space but invisible to the others. We and everything we see are tuned to our universe's particular frequency of existence, blind to the countless others that might be humming beside us. The idea also plays with our understanding of what nothingness really is. When we look into empty space, we see vast distances filled only with a thin haze of gas and radiation. But if ghost universes truly share our location, then space is not empty at all. It's crowded with overlapping realities. The void between galaxies might be teeming with structures from other dimensions, invisible yet gravitationally present. What appears as stillness could be an intricate superposition of multiple cosmic layers, all unfolding at once. If our universe overlaps with others, then there is no true edge in space, no frontier where reality ends. Instead, existence becomes a layered phenomenon, like an infinite stack of overlapping films, each containing its own version of time and matter. The higher dimensional bulk in which these brains float could be the ultimate background of reality, a realm so vast and abstract that our language and physics can barely describe it. The fifth dimension, in this sense, is a new kind of separation altogether. It divides realities not by distance, but by state. The same point in our universe could correspond to countless different points in other universes, all sharing the same coordinates in three-dimensional space, but differing along this hidden axis. To an observer confined within one brain, those others would be undetectable. But in the full multi-dimensional picture, they'd be right there, parallel and eternal. Speculative as this may sound, some theoretical models support it mathematically. Certain versions of brain cosmology, like the Randall-Sundrum models, suggest that our universe could indeed be one of many stacked along an extra dimension, with gravity acting as the only bridge between them. It's a haunting image, an entire multiverse of overlapping worlds, silent and unaware of each other, sharing the same cosmic space. They wouldn't collide or mix because their particles exist in different dimensional states, like ships passing in the night but on separate oceans. Yet their presence might be written subtly into the shape of spacetime itself. The gentle pull of gravity, the faint curvature of distant light, the quiet hum of the cosmos could all be echoes of these unseen neighbors. To stand under a starry sky and imagine that unseen universes could be layered through every inch of space, that another world could be passing through this same spot as you breathe, is to glimpse how small and strange our place in existence might be. The cosmos may be a vast multidimensional tapestry, each thread an entire universe woven beside countless others, bound together by a geometry that hides more than it reveals. The space we call empty may in truth be the most crowded place there is. The mirror universe paradox. In physics, time is not as simple as the ticking of a clock. The equations that describe how particles move or how forces interact work perfectly well in both directions. If time ran backward, those equations would remain valid. Yet in our daily experience, time feels like a one-way street. Everything moves forward, memories are of the past, and broken glass never unshatters. This arrow of time, so fundamental to human perception, remains one of the deepest puzzles in cosmology. Why does time have a direction at all? And could another universe exist where it flows the opposite way? The idea of a mirror universe, where time runs backward, arises naturally in certain cosmological models that attempt to make sense of symmetry, one of nature's most sacred principles. In physics, symmetry is not just aesthetic, it's a rule book. Every fundamental interaction seems to conserve something: energy, momentum, charge, and often these conservation laws come from deeper symmetries of the universe. If our universe began from an initial state of perfect symmetry, then perhaps time's direction itself should be balanced too. One half of the cosmos would evolve forward in time, the other backward, each a mirror reflection of the other's thermodynamic fate. This idea was given mathematical form in the two-headed time model proposed by some theoretical physicists, including Sean Carroll and Jennifer Chen in the early 2000s. Their work suggested that the Big Bang might not have been a singular beginning, but rather a middle point, a state of lowest possible entropy from which two universes expanded in opposite temporal directions. To an observer on one side, us, entropy increases as time moves forward. To an observer on the other, their time would also seem to flow forward, from their perspective, though to us it would appear reversed. In this view, both universes experience their own normal sense of causality and progression. It's only from a higher dimensional perspective that the two are mirror images of each other. This model elegantly explains why time seems to move only forward in our universe. The flow of time isn't a fundamental property, it's a consequence of entropy increasing from an initially low entropy state. Entropy, the measure of disorder, gives time its arrow. As systems evolve, they naturally move from order to chaos because there are simply more ways for things to be disordered than ordered. The early universe, tightly packed, uniform, and hot, was remarkably low in entropy. As it expanded and cooled, structures like stars and galaxies formed and entropy began to rise. But if the Big Bang was truly a symmetric event, that low entropy point could be a pivot, a hinge between two universes each experiencing increasing entropy in opposite time directions. To visualize it, imagine an hourglass flipped in the middle of time. At the narrowest point, the Big Bang, both halves begin to flow outward but in opposite directions. In one, time ticks forward, in the other, backward. Neither can perceive the reversal because their respective arrows of time are self-consistent. The mirror universe isn't rewinding our history, it's evolving forward according to its own thermodynamic law. But from a grand perspective, the total system, the two universes together, maintains perfect symmetry. If the Big Bang was not a true beginning but a transition or balance point, then the notion of before becomes meaningless. Our universe would not be the aftermath of a single explosion, but one side of a grander time-symmetric reality. In that sense, both universes could be thought of as each other's pasts, connected not causally but symmetrically through the laws that govern entropy and spacetime. Certain versions of the mirror universe hypothesis propose that for every particle in our universe, there exists a mirror counterpart in the time-reversed one. These mirror particles would obey the same physics, but with reversed charges or interactions. The two universes would be exact opposites in every measurable way, maintaining the balance of the cosmos. Our matter would correspond to their antimatter, our expansion to their contraction, our future to their past. Together, they might represent the universe's ultimate equation, zero. Physicists often describe the total energy of the universe as potentially adding up to nothing. The positive energy of matter and radiation might be exactly balanced by the negative energy of gravity. If the universe truly sums to zero, then perhaps time itself must also be balanced, flowing in opposite directions across a cosmic divide. This idea aligns with the concept of CPT symmetry, or charge, parity, and time reversal, a cornerstone of quantum field theory. CPT symmetry states that if you reverse the charges of all particles, flip spatial coordinates and reverse time, the laws of physics remain unchanged. A mirror universe could be nature's way of enforcing that symmetry on the largest possible scale. Detecting evidence for such a mirror universe would be extraordinarily difficult. Since the two universes are separated by time's direction rather than physical space, no information can cross between them. Causality itself prevents it, just as we cannot send a message to our own past. However, our universe seems to have far more matter than antimatter, even though the laws of physics predict they should have been created in equal amounts. Some cosmologists have suggested that this imbalance could be explained if the missing antimatter exists in the mirror universe. From a symmetric standpoint, both sides would contain equal quantities overall. We see mostly matter, while the other universe would see mostly antimatter. The two would balance perfectly across the divide. If there truly exists a universe where time runs backward, then what does that say about our concept of cause and effect? In our universe, causes precede effects, but in theirs, the reverse would be true, though still internally consistent. Their history would unfold in reverse relative to ours, but from their perspective, it would feel just as forward-flowing and logical. It forces us to reconsider whether the flow of time is an objective feature of the universe or a subjective one, a product of how beings like us perceive entropy's gradient. Some even wonder whether consciousness itself is tied to the direction of time. Could a being in the mirror universe experience awareness in reverse, remembering what we call the future and anticipating what we call the past? Our biology, our memories, even our sense of identity are built upon increasing entropy, the formation of memories, the burning of energy, the irreversible nature of thought. A reversed flow of time might produce a reality so alien that it defies comprehension. Such thought experiments reveal just how narrow our understanding of reality might be. We inhabit one temporal direction and assume it's universal, but nature may not be so limited. Time could be a local phenomenon, a direction chosen by circumstance, not decree. Somewhere beyond the boundary of our perception, another cosmos may exist, perfectly balanced, its galaxies unwinding even as ours unfold, its stars dimming as ours ignite, its beings perhaps pondering their own arrow of time and wondering if another universe exists where everything runs the other way. The negative energy frontier. In general relativity, energy and mass tell spacetime how to curve, and spacetime tells matter how to move. Normally, this relationship produces what we see all around us, gravity, pulling things together. Positive energy bends space inward, creating attraction. But in the equations, nothing forbids the opposite sign. If energy could somehow be negative, it would bend spacetime outward instead, repelling rather than attracting. Instead of collapsing space, it would stretch it, making the geometry of the universe behave in unexpected, even paradoxical ways. In ordinary experience, we never encounter such energy. Everything we know, stars, planets, people, carries positive energy. Negative energy, if it exists, belongs to the quantum world. In quantum field theory, the vacuum seethes with activity, with virtual particles popping in and out of existence too quickly to be observed directly. These fluctuations sometimes create regions where the energy density dips below the normal vacuum level. Those are the tiny, fleeting glimpses of what might be called negative energy, places where the nothingness of space briefly becomes less than nothing. Physicists have actually observed effects that seem to require negative energy, though only in minuscule amounts. One of the most famous examples is the Casimir effect, discovered in the mid-20th century. When two uncharged metal plates are placed very close together in a vacuum, they experience a faint but measurable force pulling them together. It happens because the plates restrict the wavelengths of virtual particles that can exist between them, lowering the vacuum energy in that gap compared to the surrounding space. The result is a pressure difference that mimics a negative energy density between the plates. It's a microscopic effect, but it shows that space itself can host regions where the energy balance tips below zero. The existence of negative energy in principle opens the door to exotic geometries of spacetime. In the 1980s, physicist Kip Thorne and his colleagues used it in their theoretical exploration of wormholes, tunnels through spacetime that could link distant points in the universe, or perhaps even separate universes entirely. According to their calculations, a stable, traversable wormhole would require a lining of negative energy to prevent it from collapsing under the crushing weight of gravity. Without that exotic matter, the wormhole's throat would snap shut faster than light could pass through. In effect, negative energy acts as a kind of gravitational counterweight, a force that pushes space apart instead of pulling it together, holding the gateway open. If negative energy could be harnessed, it might not only allow shortcuts through our own universe, but also open doorways between universes. Some cosmologists suspect that the separation between universes in the multiverse might itself be maintained by zones of negative energy. These boundaries could act like cosmic membranes, regions where space-time is warped so strongly that light and matter from one side can never cross to the other. They wouldn't be walls in the traditional sense, but energetic gradients marking the edges of distinct realities. In inflationary cosmology, this idea gains even more context. When the early universe expanded faster than the speed of light during inflation, it did so because of a peculiar kind of energy, one with negative pressure. This negative pressure drove space to stretch exponentially. When the inflationary field decayed, it released its stored energy as heat, forming the particles and radiation of the universe we see today. In this picture, negative energy, or something very much like it, is the fuel for creation itself, an engine that both inflates and divides reality across an eternal landscape. The uncertainty principle allows brief violations of energy conservation as long as they happen fast enough that the universe forgives them. For an infinitesimal instant, a quantum fluctuation can borrow energy from nothing, and sometimes what it borrows is negative. These transient pockets might be tiny seeds of curvature in space-time. Some theorists imagine that if one of these fluctuations was somehow amplified, it could inflate into a full-fledged universe. However, there are deep limits to what physics allows. Theorems known as quantum inequalities suggest that while negative energy can exist, nature enforces strict bookkeeping rules. You can't create it in unlimited amounts or sustain it indefinitely. For every region of negative energy, there must be compensating positive energy nearby, balancing the total. This prevents paradoxes like creating perpetual motion or tearing space-time apart at will. Yet, even within these limits, small pockets of negative energy could have profound effects, bending light, distorting time, or shaping the topology of space in subtle ways that might one day be detectable. The interplay between negative and positive energy may even help define what we call reality. In quantum field theory, the vacuum is filled with potential. The line between something and nothing becomes blurred, depending on the observer's motion and the curvature of space-time. In curved regions, such as near black holes or at the edge of expanding universes, this shifting balance could create observable effects. Hawking radiation, for instance, emerges because quantum fluctuations near a black hole's event horizon separate into pairs. One particle escapes as radiation, while its partner falls in with negative energy, reducing the black hole's mass. In a strange sense, black holes evaporate because they feed on negative energy. If this process can occur near the edge of a black hole, could something similar happen at the edge of a universe? Perhaps the fabric of space-time itself interacts with neighboring realms through such exchanges. Negative energy might act as the mediator, the invisible currency that allows the cosmic balance to hold across multiple universes. Some speculative models propose that universes could trade energy across higher dimensions, with negative energy serving as the counterpart to positive energy flow. When one universe expands, another might contract. When one gains energy, another might lose it. The multiverse would be a closed economic system of existence, maintaining equilibrium through exchanges we can never directly observe. In our universe, horizons, whether of black holes or the cosmic background, are limits to information. What lies beyond them may still exist, but it is forever hidden from view. If negative energy defines such horizons, then it might also define the invisible borders between universes. The regions where space-time stretches fastest, where quantum fields fluctuate most violently, could be where realities diverge. each sealed from the others by an energy gradient that prevents overlap. In the realm of theory, researchers exploring quantum gravity often encounter negative energy as a necessary ingredient. The equations describing the early universe or the birth of spacetime from a quantum vacuum frequently include terms that behave as if energy density were negative. These solutions seem to suggest that negative energy is woven into the structure of reality. It is what allows expansion to occur, curvature to stabilize, and perhaps universes to remain distinct yet contiguous, like soap bubbles sharing a film of invisible tension. If negative energy is indeed the thread between universes, then every quantum fluctuation, every curvature of space might carry the fingerprint of other realities. It would mean that our universe's isolation is an illusion, a consequence of how energy organizes itself. We exist within a pocket of stability, surrounded by layers of exotic space-time where energy's sign flips, where the laws of physics bend toward the impossible. Those regions might be the true frontier of the cosmos, not distant galaxies or black holes, but the unseen gradients of energy that quietly sculpt the architecture of all existence. Could a white hole be a window? If black holes represent the ultimate one-way trap, white holes are their mirror opposites, objects that nothing can enter, only escape from. In theory, a white hole would eject light and matter, but allow nothing to approach it, like a cosmic fountain in reverse. It sounds fantastical, and indeed no white hole has ever been observed. Yet the mathematics that predict black holes also allow white holes as valid, though extreme, solutions. If black holes exist, and we now know they do, then their opposites might also be possible. The question that lingers is not just whether white holes exist, but what their existence would mean for the nature of space, time, and the boundaries between universes. If you take the description of a black hole and run it backward, you get another valid solution, the white hole. A black hole forms when matter collapses inward, curving space-time so severely that nothing can escape once it passes the event horizon. A white hole, by contrast, would appear to explode outward, flinging energy and matter into space while forbidding anything from crossing inward. If the two were connected, matter falling into a black hole might, in some distant region or another universe, emerge from a white hole. One end devours, the other gives birth. When this symmetry was first noticed in the early 20th century, it was treated as a mathematical curiosity. But as physicists studied the equations more closely, they realized that the black hole and white hole could, in theory, exist in the same spacetime structure, connected through a tunnel known as an Einstein-Rosen bridge. This bridge, better known today as a wormhole, would link the interior of a black hole to the exterior of a white hole. Anything that fell into the black hole could, in principle, emerge from the white hole elsewhere. In this idealized version, space and time curve to form a passageway through the universe, or perhaps between universes. Of course, that elegant picture immediately runs into trouble when real physics is applied. In the real universe, black holes aren't eternal smooth structures. They form from collapsing stars. The process is messy, full of turbulence and radiation. There's no sign of a corresponding white hole at the other end. The moment the star's core collapses past its Schwarzschild radius, its matter and light are lost to the outside world. Observers see nothing but the event horizon and over time the black hole's slow evaporation through Hawking radiation. The equations that describe white holes require a level of perfect symmetry that nature rarely grants. Yet even so, the concept remains compelling, especially when extended beyond ordinary astrophysics. In the 1960s and 70s, theorists began exploring whether the early universe itself might have behaved like a white hole. The Big Bang, after all, shares a peculiar resemblance. It was a moment when space, time, and matter seemed to burst outward from a highly compressed, energetic state. Some have even described the Big Bang as a kind of cosmic white hole, an explosion from which everything we see emerged, while nothing could enter. In that sense, our entire universe could be the other side of a black hole that formed elsewhere. This idea gains further intrigue when considered alongside quantum gravity and the information paradox. According to classical physics, Anything that falls into a black hole is gone forever. But quantum mechanics insists that information can never be truly lost. That contradiction has driven decades of debate, leading to theories that black holes might somehow encode or release the information they consume. If that's true, one possible escape route is through a white hole, a mechanism for information to re-emerge. In such a model, the death of a black hole, through Hawking radiation or other quantum processes, could give birth to a white hole on the other side of spacetime. Some physicists have tried to model how that might work. In certain loop quantum gravity theories, the singularity at a black hole's core may never actually form. Instead, spacetime compresses to an extreme but finite density, then rebounds. The rebound would reverse the collapse, turning the black hole into a white hole. Matter and energy trapped inside would then be expelled, not destroyed. The timescale for such a transition could be enormous, perhaps billions or trillions of years, but in the grand timeline of the universe, it could still happen. A black hole could one day become a white hole, releasing everything it once consumed, transformed but not lost. That picture offers a curious form of cosmic recycling. Every black hole eventually could be a gateway. Not a gateway one could travel through, but a transformation point in space-time where information is released into another domain. To an observer in our universe, the process would be slow and faint. To someone or something on the other side, it might look like a sudden eruption of energy. In that view, every black hole could be the seed of creation somewhere else, and every white hole the echo of a collapse from beyond. According to our understanding of thermodynamics, white holes would be highly unstable. Any small disturbance, even a single stray particle approaching the horizon, could disrupt the delicate balance needed to keep the outward flow pure. Because nothing can enter a white hole, it has no way to absorb such disturbances. It would collapse under its own contradictions. That's one reason many physicists regard white holes as purely mathematical constructs, rather than physical entities. Recent research has found new ways to keep the idea alive. Some theoretical models propose that white holes could exist for extremely short times at the quantum scale, as brief bursts of radiation. These Planck-scale white holes would be far too small to see, but they might represent moments when spacetime briefly flips from collapse to expansion. If true, they could play a role in processes like black hole evaporation, where the final stage might involve a quantum bounce, the black hole turning inside out and releasing its energy as a white hole explosion. There are also hypotheses that connect white holes to the mysterious phenomena we call fast radio bursts, or FRBs, powerful, millisecond-long flashes of radio energy that appear randomly across the sky. Some have speculated, though without evidence, that these bursts could be signatures of small white holes releasing pent-up energy. It's a wild idea, but not an impossible one. The cosmos remains full of brief, unexplained signals, and while most are likely from astrophysical sources like neutron stars or magnetars, the possibility that one could trace back to a white hole keeps imaginations alive. Mathematically, the equations describing black and white holes are two sides of the same coin. The difference lies in direction. This reversal means that from our point of view, a white hole would appear to violate causality, releasing matter before any event could have caused it. They might reveal something about how time itself can bend or even loop in extreme conditions. In the farthest reaches of theoretical physics, where quantum mechanics and relativity begin to merge, time may not be as linear as it appears. In such a framework, the birth of a white hole could be the mirror image of a black hole's death, the same event seen from different directions in time. The event horizon of a black hole marks the point of no return. A white hole, by contrast, would mark a horizon of no approach, a region forever pushing outward. Between them could lie the thin bridge of a wormhole, connecting distant regions of space or entirely separate realities. That bridge may be unstable or purely theoretical, but its existence in mathematics hints at a universe far richer in structure than what we observe. If such gateways exist, where do they lead? Do they simply open into other parts of our universe or into new universes entirely? Could a white hole be a window through which the contents of one cosmos flow into the birth of another? Some cosmologists find that idea tempting because it ties together multiple mysteries at once: the origin of the universe, the fate of information in black holes, and the possibility of other realms beyond ours. It would mean the cosmos is not a closed story, but an interconnected network of births and deaths, each event a passage between realities. Observationally, we have no evidence for white holes, but the universe has surprised us before. Black holes themselves were once dismissed as mathematical oddities. For decades, they were considered too absurd to exist. Then we found them everywhere, in binary systems, in galactic centers, even merging in the depths of space. If their opposites exist, they may hide just as quietly, waiting for the right conditions to reveal themselves. The black hole multiverse hypothesis. Some cosmologists have proposed that each black hole could be the seed of another universe. In this view, the crushing gravitational collapse that occurs when a massive star dies doesn't lead to an infinite singularity of destruction, but to the birth of something else. A new region of spacetime that buds off from our own. To an external observer, the black hole appears as a sphere of darkness. To whatever lies beyond, it could appear as a Big Bang. This is the essence of the black hole multiverse hypothesis, a theory that suggests the cosmos itself may be an endless branching tree of universes, each growing from the death throes of stars in another. The idea emerged from attempts to solve one of the deepest puzzles in physics, the problem of singularities. In classical general relativity, the equations predict that inside a black hole, all matter collapses to an infinitely dense point where the laws of physics break down. But infinities in physics usually signal a missing piece of understanding rather than a physical reality. Many theorists believe that quantum gravity might smooth out these infinities. Instead of a singularity, the core of a black hole could be an incredibly dense but finite region, where space and time are compressed into a kind of cosmic bridge. On the far side of that bridge could lie a baby universe, a self-contained expansion of space-time disconnected from its parent. This concept draws inspiration from the equations of cosmological inflation. If that inflationary process can occur once, perhaps it can occur again, in miniature, inside the gravitational shell of a black hole. As matter and energy fall inward, their density and temperature rise until they reach a threshold that triggers inflation. From that moment, the new universe begins expanding internally, sealed off by the event horizon. To an outside observer, the black hole remains a static point of no return. To an inside observer, if such a being could exist, their entire cosmos would appear to be expanding outward from a singular beginning, never realizing that their Big Bang was born in the collapse of a star elsewhere. The Russian physicist Igor Novikov and others in the 1960s first toyed with this concept in theoretical form. Later, Lee Smolin developed what he called the fecund universe hypothesis, where black holes not only spawn new universes, but also subtly pass on their physical properties, their constants of nature, to their offspring. In Smolin's picture, universes reproduce through black holes in a kind of cosmic natural selection. Those that are more efficient at creating stars and therefore black holes leave behind more descendants. Over cosmic time, universes that favor black hole production would dominate the multiversal population. This idea links the structure of physical law, things like the strength of gravity, the mass of the proton, or the cosmological constant, to a grand evolutionary process. From our perspective, such a model could even help explain why our universe's laws seem finely tuned for the formation of stars and galaxies. It might not be coincidence, but inheritance. Just as biological life adapts over generations, universes could evolve toward configurations that allow for continued reproduction. Our universe might simply be one of many that stumbled upon a recipe conducive to its own regeneration. Each black hole it contains could represent a doorway to the next generation, forever hidden from view by its own horizon. If space and time truly bend inward and form a new domain, what connects the two? The interior of a black hole could, in principle, form an Einstein-Rosen bridge, but most wormholes are unstable. Without some form of negative energy to hold them open, they would collapse before anything could pass through. This means that the black hole universe connection might not be a traversable bridge, but a topological branching. Even if this occurs, no information or matter from our side could cross back. The new universe would exist in its own causal bubble, expanding internally while sealed off from ours. The event horizon would act like a membrane separating parent and child, allowing only the gravitational imprint to remain. This might explain why black holes in our universe seem to lose information. If the information isn't destroyed, but rather transferred into a new universe, it may not be lost at all, merely inaccessible from our perspective. Some physicists find this idea appealing because it allows information to be preserved globally across the multiverse, even if it appears to vanish locally within any given universe. Others, however, caution that the hypothesis remains deeply speculative. There is currently no way to test whether the interior of a black hole connects to another cosmos, and the extreme conditions near the event horizon make direct observation impossible. Even the most powerful telescopes can only observe the outskirts of these gravitational wells. If black holes truly create new universes, then perhaps certain physical constants in our universe could bear statistical signatures of that process. Smolin's model, for example, predicts that universes maximizing black hole formation would cluster around certain parameter ranges. Comparing those predictions with the observed values of physical constants could offer hints, though not proofs, that cosmic reproduction is occurring. Some cosmologists also wonder whether the birth of a new universe could leave a faint imprint on its parent, perhaps in the form of gravitational echoes or quantum fluctuations near the horizon. Mathematically, the concept ties into loop quantum gravity and other approaches that attempt to quantize spacetime. In some of these models, the collapse inside a black hole never leads to a singularity, but reaches a minimum volume, a bounce. If that's true, the entire cosmos may be engaged in a recursive process of creation and collapse, each universe giving rise to the next through gravitational implosions that recycle matter, energy, and physical law. If every Big Bang is the aftermath of another universe's death, then perhaps there never was a true origin, only a continuous chain of transformation stretching indefinitely backward and forward in time. What we call creation might simply be the other side of collapse. Falling through the singularity. Outside a black hole, space and time still behave in ways we can roughly imagine. The gravitational field grows stronger as one approaches the event horizon, but clocks still tick, light still moves, and cause still precedes effect. Then, as one crosses that invisible boundary, something remarkable happens. The roles of space and time exchange. Within the horizon, moving forward in time means moving deeper inward. The center becomes inevitable, not a place one can steer away from. Every path, every future leads toward it. The equations predict that, at the core, density becomes infinite, and curvature infinite as well. But infinities in physics rarely describe the real world. Just as Newton's laws fail at the speed of light, Einstein's equations may fail at the singularity. When matter is compressed beyond any known limit, quantum effects can no longer be ignored. Something new must emerge in place of the singularity, and that something may change our understanding of what lies within. Instead of a point of infinite collapse, some theories suggest a minimum volume where space-time itself resists further compression. If that rebound connects to a new expanding region, the singularity transforms from a terminal point into a bridge. If this is true, the journey through a black hole is not a plunge into oblivion, but a passage to creation. The singularity becomes the narrowest point of a funnel connecting two domains of space-time. The mathematics of such connections appear in solutions to Einstein's equations known as Kruskal-Szekeres extensions. These describe a maximally extended black hole, showing that beyond the event horizon lies not a single universe, but multiple regions, some connected through what look like tunnels of spacetime. In these models, a traveler falling inward could, in principle, continue past the singularity into another domain. Whether that continuation is physically meaningful or merely a mathematical artifact remains an open question. The question of what an observer would actually experience during this fall is one of both fascination and impossibility. For an outside observer, the traveler would never seem to cross the horizon at all. Time would appear to slow infinitely as the gravitational redshift stretches each signal into oblivion. But for the one falling in, the experience would be very different. Their time would continue normally, their descent accelerating faster and faster. The stars of the universe above shrinking into a distant halo of light. Within moments, according to their own clock, they would reach the center. At that point, relativity predicts destruction. Tidal forces would stretch and compress them until atoms themselves are torn apart. Yet if quantum gravity intervenes, the interior may not crush everything to nothingness, but transform it. Some researchers, like physicist Nikodem Poplawski, have proposed a model in which every black hole gives birth to a new universe on the other side of its core. In this Einstein-Cartan theory, spacetime is not perfectly smooth but possesses a property called torsion, tiny twists that become significant at extreme densities. These twists generate a repulsive force that prevents the formation of a true singularity. Instead, the collapsing matter rebounds, creating a new expanding region. Poplawski's equations show that this bounce could naturally lead to a universe with its own arrow of time and physical constants. In such a scenario, the act of falling through is not something that any object or person could survive or observe. The process occurs beyond the limits of our perception and outside the reach of light. But it changes what we mean by inside. The singularity becomes a membrane separating realities. Each universe could be nested within another, like cosmic matryoshka dolls, each black hole a gateway to a deeper layer of existence. The chain might stretch infinitely backward. Even within the abstract world of mathematics, the idea remains controversial. Classical general relativity cannot describe a passage through the singularity because it predicts that space-time curvature diverges there. To go beyond that limit requires a fully quantum theory of gravity, something physicists have pursued for decades but not yet achieved. String theory offers one possible framework. In some string models, the singularity may be smeared out across these dimensions, avoiding infinities and permitting smooth transitions between collapsing and expanding regions. Yet without experimental access, these ideas remain speculative. We cannot peer inside a black hole to see what happens beyond the horizon. Even the most detailed simulations rely on approximations and assumptions. Still, indirect clues could one day emerge. Researchers have searched for these signatures, and while none have yet been confirmed, the search continues. Entangled realities. Quantum entanglement has long stood as one of the most baffling phenomena in all of physics, a quiet rebellion against our intuitive sense of distance, separation, and cause. When two particles become entangled, their properties become linked so deeply that measuring one instantly determines the state of the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, a phrase that captured both admiration and discomfort. In his view, nature shouldn't allow such instantaneous connections across space, yet experiment after experiment has shown that it does. Over the decades, entanglement has gone from being a philosophical oddity to a cornerstone of quantum information theory, used in quantum computing, teleportation, and cryptography. If entanglement is not limited by space or time, could it also extend beyond the boundaries of our universe itself? At first, the idea sounds too speculative to take seriously. But some physicists have begun to explore whether the deep mathematical structure of entanglement could reach farther than we realize, perhaps even linking separate universes together. The logic begins with the observation that entanglement is not a force or a signal moving through space. Rather, it's a shared quantum state that exists across a system as a whole. There's no need for particles to send messages faster than light, because they were never truly independent in the first place. If the wave function describing reality were ever to encompass more than one universe, entanglement might naturally bridge the gap. The notion gains a sliver of plausibility when one considers how multiverse theories describe the formation of new universes. In some cosmological models, such as the inflationary multiverse, countless universes bud off from an inflating cosmic background, each forming its own bubble of spacetime. If these bubbles emerge from a shared quantum field, then in principle they might inherit quantum correlations, faint threads of entanglement that link them across the higher dimensional vacuum. In this view, entanglement would not stop at the edges of a universe, because there would be no true edge in the quantum description. The entire multiverse would be one vast wave function, with each universe being a branch of it. This idea has led some researchers to propose that entanglement could be the most fundamental structure in existence, more basic than space or time themselves. In certain formulations of quantum gravity, space-time isn't a fixed background, but something that emerges from the pattern of entanglement among underlying quantum elements. The geometry of reality, in this sense, is woven out of the connectivity of quantum information. If that's true, then the separation between universes could be more about the degree of entanglement than about physical distance. Universes that are entirely unentangled would be causally sealed off from one another, while those sharing a sliver of entanglement might subtly influence each other through deep, non-local correlations that we cannot yet detect. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a bold conjecture now known as ER equals sine EPR, connecting two of physics' most mysterious ideas, Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement. Their proposals suggested that an entangled pair of particles could be thought of as being connected by a microscopic wormhole, not one that could be traversed or used to send messages, but one that expresses the same underlying mathematics. In other words, entanglement is a form of connection through space-time, just not in the classical sense. If this relationship holds universally, then every pair of entangled particles might be linked through tiny quantum bridges, forming a vast hidden network beneath the visible structure of the cosmos. Extending that logic one step further leads to a startling implication. If universes themselves can become entangled, then they might be connected through larger-scale analogues of these quantum bridges. Some cosmologists have proposed that if our universe originated as a quantum fluctuation within a larger multiverse, its initial conditions might retain traces of entanglement with its parent universe. Those traces could manifest as slight irregularities in the CMB or as unexplained correlations between distant regions of space that appear too uniform to have ever interacted causally. In other words, if the early universe was born quantum entangled with something beyond it, the echoes of that connection might still linger in the radiation that fills our sky. Some have speculated that quantum entanglement could act as the only bridge between otherwise inaccessible realities. Unlike wormholes, which require exotic matter and immense energy to stabilize, entanglement is a natural feature of the quantum world. It doesn't require construction, it simply is. If the multiverse is real, entanglement might be the subtle fabric that ties it together, a hidden network of instantaneous correlations linking all branches of reality. Yet from within any one universe, those connections would be invisible, detectable only through their indirect influence on probabilities and symmetry. If all universes are part of one grand entangled system, then individuality itself, of particles, of systems, even of entire realities, might be an illusion created by the limits of observation. What we call our universe could be one branch of a cosmic wave function that has decohered from the rest, appearing separate because quantum interference between branches has become negligible. But fundamentally, it would still belong to a greater whole. This aligns with the many worlds interpretation of quantum mechanics, which posits that every quantum event causes the universe to branch into multiple outcomes, each existing in its own version of reality. Under that interpretation, entanglement doesn't stop at small scales. It is the very mechanism by which entire universes split and coexist. The key difference here is perspective. In the standard view, Entanglement operates within a single universe, connecting particles that once interacted. In the extended view, entanglement is the underlying relation between universes themselves, the scaffolding that holds the multiverse together. It's as if reality were not a collection of independent worlds, but one enormous, self-connected structure of quantum information, folding in on itself infinitely. Every universe would be a different expression of the same wave function, evolving according to its own internal decoherence, but still bound by shared quantum roots. For now, our tools are far too primitive to test any of this directly. But the notion that entanglement could link realities isn't entirely beyond reach. Quantum experiments have already pushed entanglement across extraordinary distances, between satellites in orbit and laboratories on Earth, across hundreds of kilometers of fiber optic cable, and even through open space. No matter how far the entangled partners are separated, the connection remains intact. There's no sign that distance weakens or slows the effect. This feature, that entanglement has no known range limit, leaves open the faint but haunting possibility that it could operate on scales we have never conceived of, perhaps extending beyond our cosmic horizon or even beyond our universe entirely. Some researchers have begun exploring what such connections might imply for cosmology. If our universe is entangled with others, it might influence how fundamental constants appear to us or how quantum fluctuations shape the large-scale structure of galaxies. Tiny deviations in those constants could be a kind of entanglement fingerprint, faintly reflecting information shared across universes. Even if we could never send a signal through such a bridge, the correlations themselves might subtly tune the character of our cosmos. In this way, the multiverse would not just be a collection of disconnected bubbles, but a living, quantum-entangled network, each universe humming in quiet synchrony with others. In the most speculative corners of theoretical physics, some have even imagined that consciousness might have a quantum aspect connected to entanglement, and that under extreme conditions, near black holes or in the deep fabric of spacetime, this entanglement could interact with other realities. It's a fringe idea, not widely accepted, but it underscores how entanglement continues to inspire thinking that stretches far beyond traditional boundaries. It reminds us that what we call the universe might not be a closed box, but a node in a much larger quantum structure. Parallel paths through quantum space. In the quantum world, a particle can be in two places at once. An atom can spin in opposite directions simultaneously, and a photon can travel through both paths of a slit experiment before revealing where it chose to go. This strange behavior puzzled even the pioneers of physics. When faced with this ambiguity, Niels Bohr described the quantum realm as fundamentally probabilistic, a place where nature itself doesn't decide outcomes until observation collapses the possibilities into one reality. But one of Bohr's contemporaries, Hugh Everett III, saw things differently. In 1957, Everett proposed the following radical idea. What if all possible outcomes actually occur, just not in the same universe? Everett's many worlds interpretation suggested that the universe never truly chooses one outcome over another. Instead, reality splits whenever a quantum event happens, creating parallel paths, each as real as the other. In one world, a photon goes left. In another, it goes right. In one version of history, an atom decays. In another, it remains intact. Every quantum decision branches reality, multiplying worlds without end. From this perspective, what we perceive as chance or probability is merely our experience of existing within one path among countless others. The other outcomes don't disappear. They unfold alongside ours, separated not by distance, but by quantum divergence. This notion fundamentally changes how we understand randomness. When you flip a coin, you expect either heads or tails. But in the many worlds interpretation, both results occur, each in its own universe. You simply find yourself in the branch where one result happened, while another version of you observes the opposite outcome. To an observer inside any given world, it feels like only one event took place. But from the larger perspective, the entire quantum state continues smoothly, encompassing all possibilities at once. The universe doesn't split in a violent explosion of energy, it quietly diverges into an ever-growing network of realities, each carrying on as if it were the only one. This branching process isn't limited to small events. Every particle interaction, every quantum fluctuation, every measurement at every scale contributes to the endless unfolding of alternate universes. The scope is staggering. Every decision made by every atom in the cosmos generates new realities. Somewhere, a supernova that never happened still burns. Somewhere else, life evolved differently on Earth, or not at all. These aren't hypothetical what-if stories, but fully realized outcomes in the mathematics of quantum mechanics. According to Everett's view, the universe is a vast, self-replicating quantum structure, constantly splitting into countless parallel paths through quantum space. Physicists often describe this process through the concept of the universal wave function, a single, immense mathematical entity that contains all possible configurations of reality. In standard quantum mechanics, this wave function collapses when an observation is made, selecting one outcome. But in the many worlds interpretation, the wave function never collapses. It simply continues evolving according to the deterministic laws of quantum physics, branching into new components as each event plays out differently. The world we see around us is just one thin strand of this vast unfolding web. For many scientists, this view is both elegant and unnerving. It eliminates the need for mysterious collapses or hidden observers, maintaining strict mathematical consistency. Yet it comes with an enormous cost, an infinite number of parallel universes, each equally real but forever inaccessible. It raises questions that blur the line between science and philosophy. If every possible version of events occurs somewhere, what does it mean to make a choice? Is free will an illusion if all possible outcomes already exist? And what defines you if there are countless copies of you living out different versions of your life across branching realities? Philosophers and physicists alike have wrestled with these implications. Everett himself argued that all versions of a person are equally valid, but our consciousness experiences only one branch at a time. When a quantum event occurs, consciousness effectively follows one path through the branching tree of possibilities. From your perspective, you only experience one timeline, yet infinite other yous continue in the others. This gives rise to a profound reimagining of fate. Not a single road stretching ahead, but a forest of diverging trails, all equally real, all equally traveled. Some interpretations of the many worlds idea suggest that the branching universes never interact after divergence. Once separated, they evolve independently, with no influence or communication between them. Others, however, speculate that under certain conditions, perhaps through quantum interference or phenomena like entanglement, nearby branches might still overlap or echo one another faintly. Some researchers even wonder if unexplained quantum anomalies could hint at faint interference between realities, though no evidence has yet confirmed this. Still, the possibility adds a haunting dimension to the theory that the boundaries between universes might not be absolute, that every so often the quantum fog might shimmer with a reflection from another path. The mathematics behind many worlds is consistent with everything we know about quantum physics. It's one of several interpretations that make identical predictions for experiments, meaning it's impossible, at least for now, to test it directly. Whether the wave function collapses or simply branches doesn't change the results we observe. Yet for many theoretical physicists, the conceptual clarity of the many worlds interpretation is compelling. It removes randomness from the universe entirely. Instead of events being truly uncertain, all outcomes happen deterministically within the full wave function. Probability becomes a matter of perspective. It describes how often an observer finds themselves in one branch versus another. In recent decades, advances in quantum information theory have given the idea new weight. Physicists studying quantum computation, for example, have noted that certain algorithms appear to draw on the simultaneous existence of many possible states, as if computation were being shared across multiple parallel realities. It's an intriguing metaphor, if not literal proof, that the quantum realm operates through overlapping possibilities. Similarly, the concept of quantum decoherence provides a mechanism for how the branching occurs. As particles interact with their environment, their quantum superpositions become entangled with countless other particles, effectively splitting the universe into distinct, non-interfering outcomes. Decoherence explains why we never see macroscopic objects in two states at once, why the world appears classical even though it's built from quantum probabilities. The many worlds interpretation also reframes our understanding of the universe's beginning. The Big Bang, in this light, wasn't a single event giving rise to one reality, but the opening act of a quantum process still branching today. Every fluctuation in the early universe, every quantum decision that shaped the formation of galaxies, stars, and planets generated new universes. The cosmos we see is just one of countless versions born from the same quantum seed. Instead of a single linear timeline, reality becomes a vast multidimensional landscape of possibilities, all existing simultaneously. It suggests that every moment of your life, every decision you make, branches the universe anew. In one world, you turned left instead of right. In another, you spoke instead of staying silent. Somewhere, every possible path you could have taken continues to unfold. The version of you reading these words is one among countless others who chose differently, each unaware of the other's existence. While deeply unsettling, the idea restores symmetry to the quantum world, treating all outcomes equally. It also resolves some of the paradoxes that arise from the act of measurement, since nothing ever disappears. Reality in this picture is not a game of chance, but a great unfolding wave of all possibilities, continuous, eternal, and complete. The only mystery left is why we experience one thread and not the whole tapestry. As speculative as it sounds, the many worlds interpretation remains a serious and respected framework among physicists. It's not a fantasy of parallel lives, but a rigorous mathematical consequence of taking quantum mechanics at face value, without adding collapse or randomness. It invites us to see the universe as a self-branching tree, where every quantum choice ripples outward forever, creating new worlds with every breath. What this means for our understanding of fate and meaning is still being debated. If all choices are realized, then moral responsibility and purpose take on new forms. It might suggest that meaning arises not from the uniqueness of outcomes, but from the particular path consciousness takes through them. In that way, your existence, here in this branch, is still singular, even among infinities. You are the awareness inhabiting one quantum path through the ever-dividing multiverse, an explorer in a sea of parallel realities that stretch far beyond imagination. If time splits, does reality follow? Time slows near massive objects and speeds up in emptier regions. Two observers moving differently through space experience different flows of time. This shows that time is not absolute, it depends on perspective. But deeper still, relativity also allows for strange geometries in which time could, under extreme conditions, loop back on itself. These are known as closed time-like curves, paths through space-time where an object could, in theory, return to its own past. If time can loop, then the idea of a single linear history begins to crumble. One could imagine a universe where events repeat, not perfectly, but with subtle variations each cycle. Each turn of the temporal loop might give rise to slightly different conditions, like ripples spreading through a pond that never truly settles. From this, one can begin to imagine not one timeline, but many, each a strand woven through the larger tapestry of space-time. In the quantum world, events don't unfold in a straightforward order. They can exist in superpositions, where outcomes are neither fixed nor sequential. A particle can interfere with its own future and past states. Some experiments have even demonstrated retrocausality, where choices made in the present appear to influence events in the past. In such a framework, time itself might not be a single directional thread, but a web of connections. with cause and effect intertwined across multiple temporal dimensions. If we combine this with the many worlds interpretation, a remarkable picture begins to form. Each quantum event, rather than collapsing into one outcome, leads to a branching of timelines. But perhaps those branches aren't spatially separate, not different universes sitting side by side, but temporally diverging paths of the same universe. Each new branch is a fork in time itself, not in space. From our perspective, we only experience one of these paths, but in the grand quantum landscape, all are real. Time, then, may not be linear, but fractal, endlessly dividing and recombining, creating an infinite structure of intertwined histories. In such a model, the past may not be a fixed point behind us. Instead, it could exist as one of many possible histories that continue to evolve as new branches form. Every moment of now might be a junction where countless futures spread outward, while the past reshapes itself to remain consistent with each path. This concept, sometimes referred to as the block universe or eternalism, suggests that all points in time, past, present, and future, coexist simultaneously within a higher dimensional structure. We perceive time as flowing because our consciousness moves through this structure in a particular way, much like a needle reading the grooves of a record. But the record itself, the full song of reality, already exists in its entirety. If we imagine time as multidimensional, the implications become even stranger. Just as space has 3 dimensions, time might have more than one. In higher dimensional time, 2 events could diverge not just forward and backward, but sideways, forming parallel temporal trajectories. Physicists have proposed that quantum uncertainty could arise from our limited perception of this multi-time geometry. What looks to us like randomness might actually be the effect of moving through intersecting temporal layers. Each moment we experience could be a cross-section of a more complex temporal manifold, a slice through an ever-branching continuum of nows. In certain approaches to quantum gravity, space-time isn't fundamental. It emerges from deeper, more abstract structures where time itself behaves differently. The two-time physics model, developed by physicist Itzhak Bars, proposes that the universe may have 2 temporal dimensions, one that governs the flow we experience, and another hidden dimension that shapes the underlying symmetries of reality. In such a universe, what we call the present might simply be one projection of a higher-order temporal structure. What we perceive as linear time would then be a shadow cast by a multidimensional process beyond our perception. There's also the idea of branching time in cosmology, where entire universes could diverge not from spatial separation, but from temporal bifurcation. In this view, the multiverse could be structured not like a cluster of parallel worlds, but like a tree of timelines, each splitting off from quantum fluctuations at the dawn of the universe. Every cosmic event could be part of a vast temporal branching structure. Some physicists have even speculated that the Big Bang itself might not have been the beginning, but a branching point in a deeper temporal fabric, a transition from one cosmic epoch to another, in a time structure far greater than our own. If time can split, then perhaps every choice we make creates a divergence, not metaphorically, but physically. In one branch we take one path, in another we take the opposite. Both are equally real, but each version of us experiences only one. Yet, if all branches exist simultaneously, then the concept of choice becomes a matter of perspective. We don't create new realities, we simply move through them. Every possible outcome of our decisions already exists somewhere in the temporal landscape, waiting for our consciousness to intersect with it. If all possible futures already exist, does that mean the flow of time and the feeling of making choices is an illusion? Some interpretations say yes, that we are simply traveling through an already written structure. Others suggest that consciousness itself is the mechanism by which new branches are realized, that awareness causes the unfolding of new temporal dimensions. In this view, reality and time co-create one another, each dependent on observation and participation. A few speculative physicists and philosophers have suggested that consciousness might not move linearly through time at all. Instead, it could skip across branches, revisiting different moments, or exploring alternate histories in ways we cannot consciously perceive. Déjà vu, intuition, or dreams, they suggest, could be subtle echoes from nearby branches, signals from versions of ourselves that diverged only slightly. If time does branch, then the universe is not a single film reel running from beginning to end, but an infinite archive of overlapping sequences. Each moment spawns countless continuations, and every continuation becomes a new source of possibilities. Our lives, our histories, and even our cosmos might be embedded within a vast, ever-expanding structure of temporal evolution, a living network of time itself. The laws of physics in this picture are not the limits of what can happen, but the rules by which time continually writes new versions of reality. In the quiet, steady flow of seconds and minutes, it's easy to believe that time is simple, a line we follow until it ends. But physics whispers that time may twist, fold, and branch in ways far beyond our senses. And if that is true, then the story of the universe is not one line, but many, woven together in a multi-dimensional tapestry that stretches across the infinite directions of time itself. Simulated universes and nested realities. What began as a thought experiment has evolved into a line of reasoning grounded in mathematics, computation, and physics. The idea is simple. Everything we see, the galaxies, the stars, the atoms, even the thoughts in our minds, might exist within an immense computational system. If that's true, then our universe could be just one layer within a hierarchy of simulated realities, each built upon the other like reflections in an endless mirror. The notion of a simulated universe doesn't mean a crude digital game or a computer as we know it. It means that, at its deepest level, reality may be built on information. Every particle, every field, and every interaction could be the product of a vast set of underlying rules, algorithms that describe how things behave and evolve. In this sense, physics and computation begin to blur. The constants of nature, the forces that govern motion, and the properties of matter could all be expressions of coded logic. To beings inside such a universe, that logic would appear as laws of physics. To whatever exists outside, they might look like lines of code running on a machine beyond comprehension. This concept gained modern form in the early 2000s through philosopher Nick Bostrom's simulation argument. He proposed that at least one of three possibilities must be true. The first is that all civilizations capable of creating realistic simulations go extinct before reaching that stage. The second is that advanced civilizations do exist but choose not to create simulations of conscious beings. The third is that such civilizations do create them, and therefore the number of simulated minds vastly exceeds the number of real ones. If that's the case, it's statistically more likely that we are living in one of the simulated worlds rather than the original. The argument rests on probability, not proof, but it forces a difficult question. How could we ever tell the difference? From within the simulation, everything would appear consistent. The laws of physics would operate flawlessly, and the digital nature of the world would be hidden beneath its apparent continuity. Yet, some physicists have wondered if certain anomalies in the structure of the universe might act as clues. For example, if spacetime is discrete, made of tiny, indivisible units rather than continuous, it might reveal a computational grid at the Planck scale, similar to pixels in a digital image. Some even speculate that the cosmic speed limit, the speed of light, could correspond to a maximum data transfer rate in this underlying system. In the quantum world, particles don't seem to exist in fixed states until they're measured. This peculiar behavior has led some thinkers to draw parallels with rendering in computer graphics, where environments are computed only when they're being observed to save processing power. While this analogy shouldn't be taken literally, it highlights how the quantum universe already behaves in a way that feels eerily similar to selective computation. If reality is simulated, then who or what is running it? The possibilities range from the mundane to the divine. Perhaps a future civilization, unimaginably advanced, has created simulations for research, entertainment, or even to preserve consciousness beyond death. Or maybe the universe we call real is itself one simulation within a nested structure, a hierarchy of realities where each level generates the next. In such a framework, even the creators might themselves be simulated, unaware that they exist inside someone else's construct. The recursion could extend indefinitely, producing a chain of realities, each one built upon the computations of the one above it. The distinction between real and artificial may not exist in any absolute sense. If simulated beings can think, feel, and experience, then their reality is subjectively as authentic as ours. From within, it would be indistinguishable from any base world. The question of which level is real becomes meaningless. Reality, then, might be defined not by its origin, but by its internal consistency, by the rules that govern perception, interaction, and continuity. Whether those rules arise from natural laws or coded instructions makes no difference to the beings that live within them. Some theoretical physicists see hints of informational structure in the way the universe behaves. The laws of thermodynamics, for instance, link entropy to information content. Black hole physics has revealed that the surface area of a black hole's event horizon encodes information about everything that falls into it, suggesting that reality itself might be fundamentally informational rather than material. To some, this sounds like the architecture of a simulation, where data describing a world is stored and processed in a form that's not immediately visible from within. Experiments have even been proposed to test aspects of this idea. Some physicists suggest that if the universe is discrete, cosmic rays traveling across billions of light years might show a subtle blurring effect caused by the resolution limit of the underlying grid. Others look for statistical patterns or noise in high-energy processes that could betray computational constraints. If nested realities exist, they could vary in their properties. Some might be tuned to simulate universes similar to ours, while others could operate under entirely different physical laws. Just as programmers design environments with specific rules, creators at higher levels might experiment with different constants, forces, or even dimensions. Each simulated universe could be a testbed for exploring cosmic evolution, consciousness, or the emergence of complexity. In such a view, the multiverse might not be a collection of naturally formed universes, but a chain of intentionally generated ones, each built by the intelligence that arose in the one before it. Some versions of the multiverse already describe endless universes budding from one another through physical processes. The simulation hypothesis replaces natural inflationary mechanisms with computational ones. New universes aren't born through cosmic expansion, but through design and execution. The two concepts, physical and digital creation, might ultimately converge, suggesting that what we call creation could be a kind of computation happening at a level we cannot reach. Thinkers for centuries have wondered whether reality is an illusion, from Plato's allegory of the cave to Descartes' skepticism about the senses. The simulation idea modernizes these old doubts, giving them a scientific form. It doesn't deny that experiences are real, but it challenges the assumption that reality must be physical in the traditional sense. If the world is a simulation, then the ultimate nature of existence might not be matter or energy, but information and consciousness, patterns interacting within a structured framework. There's an existential dimension to the theory. If we are simulated, what does that mean for purpose or meaning? For some, it diminishes the significance of life, reducing it to a computational artifact. For others, it deepens the mystery, suggesting that existence is part of a deliberate act of creation, even if by unknown beings. Would the creators be responsible for the suffering and joy of those inside? Would they even be aware of the consciousness their simulation produces? And if we someday create our own simulated realities populated by sentient beings, would we become the gods of new universes ourselves? Some scientists approach the idea from a more pragmatic angle. Whether or not we live in a simulation, the universe behaves as though it is rule-based, quantifiable, and mathematically consistent. That makes it possible to model, predict, and manipulate. If reality is computation, then perhaps understanding its code, the underlying algorithms of physics, could someday allow us to modify or transcend them. Advanced civilizations, if they exist, might already know how to navigate between levels of simulation, moving from one reality to another by rewriting the conditions of their own existence. The question of what is real becomes not about what exists independently, but what can sustain experience and coherence. A simulated universe is still a universe. Its stars burn, its atoms vibrate, its beings live and wonder about their place in the cosmos. Whether those phenomena emerge from physical fields or lines of computation may not matter to those within. To them, to us, it is reality. If every reality is defined by the perspective of those who inhabit it, then nested simulations, physical universes, and even hypothetical higher realms all share one thing in common. They are self-consistent worlds of experience. Somewhere above or below us, others might be running their own universes, just as we may someday run ours. The hierarchy could be infinite, each level unaware of the one beyond, each convinced that its world is the only one that truly exists. Yet from a higher vantage point, they would all be part of a single grand architecture, a cosmos not just of matter and energy, but of realities. Gravitational echoes from other realities. When two black holes collide, when neutron stars crash together, or when space itself shudders under immense energy, those events send out gravitational waves. First predicted by Albert Einstein in 1916 and finally detected a century later by LIGO, these waves are not light or matter. They are vibrations of reality itself. And just as sound can reveal a room's unseen corners, gravitational waves may reveal parts of the cosmos that light can never touch. Gravitational waves are unlike any other signal we can observe. While light scatters and fades when it encounters dust or matter, gravitational waves pass through everything almost unhindered. They can carry pristine information about cataclysmic events from billions of years ago. That purity makes them a perfect candidate for exploring not only distant galaxies, but also the fundamental structure of the universe itself. When LIGO first detected the tiny oscillation of a laser beam caused by a passing wave, it opened a new kind of astronomy, one that listens instead of looks. But as detectors become more sensitive, scientists have started to wonder, what if some of the waves they eventually hear aren't from stars or black holes at all, but from something beyond the reach of our cosmos? To understand how that might be possible, one must first imagine the universe not as an isolated bubble, but as part of a grander, higher dimensional space, a multiverse ocean. Unlike light or matter, which remain confined to our universe, gravity might leak out, or in. That would mean gravitational waves could occasionally cross the invisible boundaries that separate one universe from another. Some models predict that such inter-universal echoes would appear not as clean, well-defined waveforms like those from black hole mergers, but as irregular, lingering signals, faint reverberations following the main wave. LIGO and Virgo have already detected subtle anomalies in a few events that seem to contain aftershocks, as if the space-time fabric were ringing longer than it should. Most scientists attribute these to noise, imperfections in the detectors, or complex behavior near event horizons. Yet a handful of researchers have speculated that they could be the first hints that space-time isn't a closed system, but a resonant medium connected to something beyond itself. If that were true, the implications would be extraordinary. A collision in one universe could send waves through the higher dimensional space, rippling across realities like the surface of a pond disturbed by a falling stone. As the wavefront passes through our universe, it could cause barely perceptible distortions, infinitesimal stretches and compressions that our most precise instruments might one day detect. These would not align with any known astrophysical source. They might arrive from no discernible direction at all. Instead, they would seem to come from everywhere and nowhere, faint, diffuse, and inexplicably persistent. To test for such signals, physicists are already pushing technology to its limits. The LIGO and Virgo detectors on Earth can detect changes in length smaller than 1,000th the diameter of a proton. Yet gravitational echoes from beyond the universe would be even weaker, perhaps billions of times fainter. Future observatories like the Einstein telescope in Europe and the Cosmic Explorer in the United States are being designed with this possibility in mind. These next-generation detectors will operate underground to shield them from vibrations and will stretch for tens of kilometers, increasing their sensitivity dramatically, but even they might not be enough. That's why scientists are also looking to space. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will consist of 3 spacecraft flying millions of kilometers apart, connected by lasers. By observing how the distances between them change as gravitational waves pass through, LISA will detect signals at frequencies unreachable from Earth. It could pick up waves from sources far older than galaxies, from the first moments after the Big Bang. If any echoes from other universes were embedded in that ancient gravitational background, LISA could be the instrument to hear them. Its sensitivity might allow it to detect the faint interference of waves, not just from cosmic events, but from the very edges of reality. If spacetime at its smallest scales is granular or foam-like, universes could be connected through quantum bridges. Gravitational waves passing near these junctions could scatter or refract in distinctive ways, producing subtle distortions in their waveform. These deviations might appear as phase shifts or spectral irregularities when analyzed with high precision. Detecting such patterns would be like finding fingerprints from an unseen dimension imprinted on the vibration of space. Others take a more cautious view, arguing that gravitational waves, while deeply revealing, will always be constrained by the geometry of our own spacetime. Even if other universes exist, their signals could never reach us directly because they would be trapped behind causal boundaries. Yet even these skeptics acknowledge that our understanding of gravity remains incomplete. The fact that gravitational waves can travel unimpeded through the cosmos, ignoring matter and energy as if they were shadows, suggests that gravity interacts with the universe in a way unlike any other force. If anything could reach across universes, they admit, it would be gravity. Gravitational waves are real, measurable, and mathematical, yet they are also the most direct expression of spacetime's fluidity, a reminder that reality itself can flex and breathe. To think that these vibrations might carry traces from beyond our cosmos transforms them from mere astrophysical tools into cosmic messengers. Every wave recorded by LIGO or Virgo might be part of a larger symphony that spans more than one universe. The possibility of gravitational leakage has even inspired some bold theoretical experiments. For example, in certain brain-world scenarios, physicists propose that miniature black holes created in particle collisions could radiate gravitational energy into extra dimensions. If such energy disappears in a way that violates conservation laws within our own universe, it could hint that part of the gravitational field has escaped into another reality. Experiments at high-energy facilities like CERN have searched for these telltale energy losses, though so far without success. In the years to come, gravitational astronomy will expand far beyond its first detections. Space-based arrays, lunar observatories, and even atom interferometers may listen to frequencies so low that they vibrate once every thousands of years. These tools will allow scientists to map the gravitational landscape of the cosmos with unprecedented clarity. Somewhere in that tapestry of signals, buried beneath the familiar patterns of merging stars and orbiting binaries, could lie an anomaly, escaping the universe, theoretical gateways. The idea of escaping the universe sounds like the most impossible of dreams yet. In theoretical physics, it is sometimes discussed with surprising seriousness. If the universe is not infinite but bounded by horizons and physical limits, then asking how one might cross them is not so different from early humans wondering what lay beyond the ocean. At the center of this idea lies a paradox. According to general relativity, the universe doesn't exist in anything. It is the arena within which everything else exists. To leave it would seem meaningless, like trying to step outside of geometry itself. But some theories suggest that the fabric of space-time could be manipulated, twisted, or folded in ways that allow shortcuts between distant regions, or even between separate universes. The most famous of these is the wormhole. Another path toward escaping the universe involves warp drives, devices that, rather than moving through space faster than light, would move space itself. The idea gained attention in 1994 when physicist Miguel Alcubierre proposed a mathematical model showing how a warp bubble could allow faster-than-light travel without violating relativity. Inside the bubble, the traveler remains stationary relative to their local space, but the bubble compresses space in front and expands it behind. This motion would, in principle, carry the bubble, and whatever is inside it, across vast cosmic distances in a fraction of the time light would take. The mathematics is elegant, but it comes with the same obstacle as wormholes. It requires negative energy to function. In theory, if a civilization could harness the quantum vacuum, they might be able to generate such exotic energy. The Casimir effect demonstrates that vacuum energy is real, though in an incredibly subtle form. The challenge would be amplifying or controlling it. If negative energy could be shaped and contained, it might allow not only the stabilization of wormholes or warp bubbles, but also the construction of gateways beyond the observable universe, portals through which matter could, at least theoretically, tunnel into a new region of space-time. Quantum tunneling provides another possible route. In the quantum world, particles don't behave like tiny solid objects, but as waves of probability. They can sometimes tunnel through barriers that would be insurmountable in classical physics. This principle underlies everything from radioactive decay to the functioning of modern electronics. Some cosmologists have extended the idea to the universe as a whole. In their models, a universe can tunnel from one vacuum state to another, a process that may even give birth to new universes. If that is true, then perhaps a sufficiently advanced civilization could learn to trigger such transitions deliberately, creating a tunnel through the quantum structure of reality. Some physicists have speculated that the ultimate path to escape might not involve physical motion at all, but information transfer. According to some interpretations of physics, information cannot be destroyed. If consciousness is a form of information, then in theory, it might be possible to transmit that pattern across a boundary, leaving the matter behind, but carrying awareness forward. The practical side, of course, is daunting. Every one of these concepts, wormholes, warp drives, quantum tunneling, vacuum manipulation, lies far beyond any technology we can imagine. But it's worth remembering that the universe itself performs these actions naturally. It expands space faster than light during inflation. It curves space-time to extremes inside black holes. It tunnels energy from one quantum state to another. If these are natural processes, perhaps they are also pathways, ones that intelligent life might one day understand enough to use. Would it even be desirable to escape our universe? The laws of physics here allow for complexity, life, and thought. Another universe might not. The constants could differ. The dimensions might not support stable matter, or time itself could behave differently. To step through a theoretical gateway could mean entering a realm where familiar concepts, light, atoms, causality, no longer exist. The arguments against the multiverse. The most common criticism of the multiverse is simple. It cannot be tested. In science, a theory is only meaningful if it makes predictions that can, at least in principle, be confirmed or falsified through observation or experiment. This objection isn't just philosophical nitpicking. It strikes at the heart of what separates science from metaphysics. Physicists like George Ellis and Paul Steinhardt have argued that the multiverse risks turning cosmology into a belief system, one that relies on mathematical consistency rather than empirical evidence. They point out that even if inflationary models, string theory, or quantum mechanics seem to imply other universes, those implications are not direct evidence. A theory might allow for the possibility of multiple universes, but that doesn't mean they're real. As Ellis once put it, If a theory predicts something that can never be observed, it's not physics, it's philosophy. Why multiply universes beyond necessity? To critics, this looks like a violation of Occam's razor, the idea that the simplest explanation that fits the data should be preferred. Supporters respond that simplicity isn't always the same as truth. If the equations naturally lead to a multiverse, it may be simpler to accept that than to invent artificial restrictions to avoid it. But the critics remain unconvinced. They argue that the mathematics may be elegant, but without physical evidence, it remains hypothetical. A model that can explain everything explains nothing, because it can never be proven wrong. If every possible outcome happens in some universe, then no observation could ever contradict the theory. This anything goes problem undermines the predictive power that science depends on. Another major criticism is that the multiverse undermines the notion of physical law itself. If each universe has different constants, particles, and dimensions, then the laws of physics are no longer universal. They become local conditions. For some philosophers of science, that's deeply unsatisfying. The strength of modern physics lies in its search for universal principles. The multiverse replaces that ideal with an endless patchwork of random variations. Critics ask, if anything is possible somewhere, then what does it mean to discover a law at all? This line of thought also affects how scientists think about the fine-tuning problem. The question of why our universe's physical constants are so precisely set to allow life. The multiverse offers a convenient answer. There are countless universes with different values, and we just happen to live in one that supports life because only such universes can produce observers like us. But many physicists find that explanation unsatisfying, even evasive. They argue it replaces understanding with coincidence. Instead of explaining why the constants are what they are, it says, they just happen to be like this here. To some, that's a retreat from science's goal of finding deeper, causal answers. Theoretical physicist Sabine Hossenfelder has been an outspoken critic of what she calls post-empirical science. Theories that rely on mathematical beauty or internal logic rather than experimental evidence. She argues that physics risks turning into a kind of theology of equations, where belief in unseen realms replaces observation. When theories stop being testable, she says, they stop being science. The multiverse, in her view, represents that danger perfectly, an elegant idea with no anchor in data. There's also a sociological dimension to the debate. Some researchers worry that the allure of the multiverse distracts from more grounded approaches. It can be intellectually seductive, vast, imaginative, and seemingly profound. But if too many resources and minds are drawn toward untestable ideas, empirical science could lose its focus. The same concern arose in the early 20th century with speculative ether theories, and more recently with aspects of string theory. The fear is that physics could become self-referential, exploring mathematical possibilities rather than physical realities. Still, not all critics reject the multiverse entirely. Some accept it as a logical consequence of certain models, but caution against treating it as established fact. For instance, physicists like Roger Penrose and Lee Smolin have proposed alternative cosmological frameworks that explain the universe's features without invoking countless unseen copies. Others focus on finding indirect evidence. These efforts remain speculative, but show that the line between belief and science is not always fixed. It can shift as technology improves. Philosophically, the objections to the multiverse also touch on deeper questions about the nature of explanation. In classical science, explaining something means reducing it to known principles or mechanisms, but the multiverse often reverses that relationship. Instead of explaining why something happens, it explains why anything could happen, and why we observe one specific version of it. Critics argue that this is a rephrasing. It replaces why with somewhere it just is. Some scientists, however, see this criticism as unfair. They point out that the same argument could once have been made against other unobservable entities, atoms before microscopes, galaxies before telescopes, gravitational waves before LIGO. The fact that something is unobservable now doesn't mean it always will be. Perhaps future physics will reveal indirect ways of confirming the multiverse. Others argue that even if it remains untestable, the concept still has value as a philosophical framework, helping scientists think beyond traditional assumptions. But this view too raises questions. If something has no possible empirical consequences, should it still be part of physics? Theoretical physics has always relied on creative leaps. Einstein's curved spacetime, Bohr's quantum jumps, Dirac's negative energy sea. Each of these began as speculation, later confirmed by observation. But the multiverse is different. It might be the first major idea that can never cross that final bridge from theory to test. For its defenders, that's no reason to abandon it. For its detractors, that's exactly why we should. Within the cosmologist community, the divide runs deep, yet both sides share the same goal: to understand the nature of reality. The disagreement lies not in the desire for truth, but in how to reach it, through observation or through the limits of imagination. What do you think is the answer? Leave your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.